Howdy everyone, and welcome back to my channel, or welcome to my channel if you're new. This is Professor Parks, PhD, and tonight I am going live with our telescope here at George Mason University. I've done this a few times in the past, so please check out those streams on my channel. Tonight I'm going to be, hopefully, looking at the Whirlpool galaxy, or M51. It's the 51st object in the Messier catalog. Hey, KJ. I don't think I have ever interacted with you before, but thank you for being here. So as I was saying, I'm going to be eventually looking at M15. Or M51, a Whirlpool galaxy, which is in fact two galaxies. It is actually a large spiral galaxy that is currently gobbling up a smaller, irregular galaxy. Probably was a spiral at some point. And the not only is the purpose of the stream is, I have a few reasons for doing this stream. The first one is, well, I just want to show people what it's like to actually do observing, particularly if you are trying to collect science observations. For this part, I'm not going to be doing any science. I'm actually trying to create a pretty picture later on. But I want to give people kind of a flavor as to what it's like to sit at a telescope and collect data. As well as during this process, I will also be talking about various astronomical things or answering any questions that folks might have. I really just want to, kind of in line with that first point, I want to make this as transparent an operation as possible. I want folks to really understand what it is that astronomers do, how these images are taken, and what they can particularly tell us. Hey, Georg. How are you? Looking at, I have it on YouTube, so I want to make sure that was muted. I hope the sound is coming in well, and I somewhat apologize for the lighting. I hate fluorescent lights, so this is generally the lighting conditions that I typically like in my office. Some low lights next to my computer. I have a halo lamp just so you guys can see me. Let me switch over. Let's see here. I think I'm going to do that. And I think everyone knows who I am. So I am going to do that. All right. So you can all see. So, all right. So right now I'm doing something not overly exciting. I am taking calibration images, which I'll explain later on. While it's doing this, we have another, I don't know, probably 5 to 10 minutes of this doing its thing. I am just going to go over what it is, or what our telescope is like, various components, things like that. Howdy, tiny captain. So first off, let me start off with this. What we have here is a webcam, let me first start off by saying, as you can see from this webcam, I am not at the telescope at present. I am 2-3 floors below the telescope in my office, as you can probably see. And I am basically, I use VNC to dial into the control computer on the roof. And so this is the control computer here, as you can see in that image, or that webcam view. And so, in order for me to do this and to make sure that, the telescope doesn't catch on fire or slam into stuff or whatever. Garrett, I am sorry to hear that you suffer from depression. As folks know, probably I do as well. Um, but I'm glad to know that you're doing well. You have the control room over here. We also obviously on the left, that is the telescope itself. That is a 32-inch Cassegrain reflecting telescope, meaning light comes in from the top of the tube, comes down, hits a 32-inch diameter mirror on the base. That light gets reflected back up to a secondary mirror near the top, and then back down through a hole in this primary mirror, down to this observing station down here. We currently have 4 instruments that I can choose from to look at the night sky. We have an eyepiece, which is this thing right here. Hopefully you can see that. Probably can't see it very well, but there it is. We have an IR camera, a camera that is specifically designed to look in the infrared wavelengths, definitely wavelengths that we cannot see with our naked eye. Specifically, we're going to be looking in the K band, if you want to look that up. That's 2.2 microns. To give you an idea, normal human vision goes from 0.4 to 0.7, 0.8-ish microns. So significantly longer wavelengths. And then on the back side of this is a webcam, which we affectionately call the planetary cam. And if you haven't already checked it out, on my channel that I posted today is a video of Venus that we took yesterday for an event we did with the Smithsonian Associates, and it's about a minute long that I've looped, and it shows Venus in a nice quarter phase. Howdy, Chris. So I have the option to pretty much use any camera that I want, or an eyepiece that I want. So eyepiece for public nights, planetary camera for public nights, and then lastly, which I haven't mentioned yet, is this behemoth right here, which is our mains digital camera, or CCD camera. It is a 4K by 4K detector. It's a bit old at this point. It's a SBIG 16 MXT, I want to say. And this little doohickey here is the filter wheel, which I'll get into later on what that means. Tiny Captain, I guess you still need to be in the same building to have at least, actually, no, I can do this, Captain, I have on occasion done this from home, while I do live close, I live about a mile from home, we folks have dialed in and not experienced a whole lot of lag issues, as far as I know. I don't know of anyone who's tried it from across the United States or even across the world. That might be an interesting idea of trying to have someone dial in from Australia. I have this really crazy plan of trying to hook up with a university in Australia and actually build 2 observatories. It's a whole thing. Anyway, off topic. The only reason why I'm actually not doing it at home as opposed to here is we've had some issues with the telescope, and I want to be on site in case those issues arise, as opposed to being at home. So anyway, what was I saying? So yeah, that's a Cassegrain telescope. This is the main digital camera, which I will be taking images of. This is the outside of the observatory, which is on a silver tower attached to the building. That's the dome. We're currently pointing in that direction. That would be the west. And this is really a view of the bottom of our telescope. One of the issues that we've had over time is basically you can see this tension cable here. Sometimes that wants to misbehave and pop off. So we want to kind of keep an eye on it. It hasn't done that in a long time. So what else are we using? I accidentally upgraded to Windows 11. Windows 11 sucks. I highly recommend you not do that, because one of the myriad of things that no longer works is I can no longer show the double monitor display on one monitor in my office, so I have to scroll back and forth. I know, petty, but still irritates me. So this is the Sky X Pro Professional Edition. It is basically a planetarium program that we can use to operate our telescope. We can operate our telescope a couple of different ways. This is the easiest way to do so. Howdy, Charlie. And what you can see here on the right is, oh, please ignore the red. I don't know what that is. I really don't like it. And yeah, I don't know. It doesn't really affect things, but just ignore that red part. It doesn't mean anything. Or at least if it has a meaning, I don't know what it is. So this is the night sky currently at our location. We have Hercules. We have, what is this? Biotes. We have Leo in here somewhere. No, this is Leo. What is that? Oh, they've got asterisms on. I hate that. Oh, this is Biotes. Sorry, this is Biotes. Regulus is around here somewhere. So Leo is right about here. And so essentially, this is as easy as point and click. So if I want to go to Arcturus, I just click on Arcturus, and then I can tell it slew, and then it'll go over there. Right now, I have it pointed at the Beehive cluster, and there's a reason for that. I know I said I was going to be looking at galaxies, but there's a reason why I'm looking at the Beehive. Which once this gets done, I can minimize that. Once this gets done, it's done. Yay! Yes, sadly, this is true. So one of the things that I've wanted to do is I've always wanted to go to Hawaii, specifically Mauna Kea, to see all the telescopes up there. And you know, before remote operations, that's basically if you had a project using one of the telescopes, which one of my colleagues does. He uses the Infrared Telescope Facility, or IRTF, and he would get to go to Hawaii to observe there. Unfortunately, because of remote operations, that's really no longer that is really no longer the case. You typically go out to the observatory once, maybe twice, to get hands-on experience, and then for the rest of the time, once you've gotten that training, you basically just dial in. So I will probably never get to go over to Hawaii and observe with one of those telescopes, which sucks. All right, so let's see. So I'm at the Beehive. Now, let me do this. Now, the Beehive cluster is, let's do that. Beehive cluster is an open cluster. Basically, what that means is that it's a small, relatively speaking, a small collection of stars that are fairly young, very blue and bright, and fairly well distributed on the sky in the sense that it's typically a large angular size structure. What that means in terms of our telescope is that open clusters are actually pretty bad objects to look at, because our field of view is 25 arc minutes. Yeah, that'll work. Is 25 arc minutes, which does not capture the entire field or the entire field of stars. But I do get a lot of these bright ones. So, and the reason why I'm doing this is because of focus. Focus. Where is my information window? Oh, it's right there. That's weird. Okay. So what I'm looking for is to basically get as nice, tight, focused images as possible. And so open cluster is great because there are a lot of stars that are not saturated, and I can get a pretty good estimation of what the focus is. What I'm looking for is this full width half max down there, or FWHM. Ultimately, what that means is I want to get that as small as possible. The smaller the value, the more in focus I am. I'm actually going to take a 5-second image. I think that I'm pretty close to focus. Pretty close to focus. In the best focus. but I want to verify that before I. 4.1, 4.4. To give you an idea, that's not great seeing. So the atmosphere, because of the fact that it's composed of dust and molecules and all that kind of good stuff, it causes light to blur out a little bit. And we refer to the amount that it blurs it out as seeing, or seeing. Good seeing is less than an arc second, meaning that you can differentiate two objects that are an arc second away from each other. This is 4 arc second seeing, which means you can only differentiate two individual objects as separate if they're 4 arc seconds away. This is crappy. This is crappy seeing. Although for our location, given our altitude and the fact that I'm on the eastern seaboard, we would expect a good night for us is about 3. So let me do this. So I'm going to knock this down to 1 and look at these brighter stars because seeing changes fairly rapidly. So what you want to do is to basically take a whole lot of images and just mentally average them. So I'm actually going to do that. I'm going to put this on a continuous loop. So I'm getting at 5990, which is basically a meaningless number. A relative number, I am okay. It takes a while for it to download. All right, I think that makes it worse. And yes, it does take a while for this thing to download images, which is annoying. Dr. Nimrod is in the house, his house. Yeah, it's definitely worse. All right. I'm going to stop this. If I were doing this in a more rigorous way, I would do this differently. I would actually subframe because that downloads faster, but I'm not overly picky. And this is astronomy, folks. This is what it looks like in practice. Seen it here first. All right, so before my best focus was around 4.4. 3.7. I think I'm going in the right direction. Focus is not only dependent on it's dependent on the atmosphere, but one of the conflating variables of one of the reasons why, or that can affect things, is 3 is temperature, and so it's gotten warmer, and so that's going to cause the focus to change. Oh, and it's highly variable, 3 to 4.3. Yay! So 3.4. All right, let's move out. I'm going to go to 60-15. 60-20? 60-20. 60-15. Is the black and white kitty sitting on? No, it is not. Unfortunately, like I said, I'm in my office, and so Luna is currently at home. Oh, well, that sucks. fact that she's off home and the fact that 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 can't be right. 6.4 point. Okay, position. Pretty sure this is shittier. Technical term. 3.5. I'm going to go back. I'm going to call it 60-10. Focusing is annoying because it really is doing it. You can automate it, but unfortunately, our autofocusing for our telescope for some reason is dumb, is really stupid, and actually doesn't work. And I haven't had the time to figure out why. But you can play with focus forever. But considering that I don't want to do that, I'm not going to. So that is the best focus that I think I can achieve. So let us get to the good stuff. Where is it? Where did you go? Aha. So I have told it. Did I tell it? Now I have told it to. Now we are going to the Whirlpool Galaxy. Let me know if the music's too loud. I observe with music, because I just do. Makes the time go faster. So as you can see, the telescope is moving. The telescope is moving towards the Whirlpool. It is now pretty much at the Whirlpool, and the dome will then automatically it's synced with the telescope, so it knows where the telescope is pointing, and so the dome slit will move accordingly and then settle right in front of the telescope. So the telescope has a clear view of the night sky. And as the telescope tracks across the sky, the dome will adjust. Will adjust such that it will keep the dome opening right in front of the telescope at all times. The reason why domes, just for if you've ever wondered why astronomers put telescopes in domes, it's because of wind. Wind will obviously shake the telescope, and ambient light, any kind of stray light, will affect the observation. So we want to keep the telescope environment as dark as possible. Tycho Brahe was the first person to put a dome around an astronomical instrument because, again, wind was affecting his meridian instruments. And I know I'm going to get copyright, blah, 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 but since I don't get money from these things anyway, I don't care. All right, so the Whirlpool Galaxy is faint. It is a bright galaxy, but it is faint to us. So I typically, when I'm trying to find an object, I just do a standard 10 seconds in the green filter. So, there we go. Please be there, 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 please, please. Yay! Of course, that's upside down. So, stop. continuous. I want one. So this is a 10-second exposure. What that means is I am looking through the green part. I'm only looking at the green part of Roy G. Biv. So I'm looking at the night sky, but I'm only looking at green light. And I've looked at this object, the Whirlpool Galaxy, for 10 seconds, meaning that the shutter is open for 10 seconds and then closes. It then downloads the image to the computer. As you can see, a lot of the background or the night sky is very bright because light pollution sucks, and you can barely even see the galaxy. The galaxy's brightness, and compared to the background, is not much. It's not high. That's why we can barely see it. But you can see the core of the Whirlpool Galaxy here, and the core of the other galaxy there. If you don't know what the Whirlpool Galaxy actually should look like, Google Hubble Whirlpool Galaxy. Beautiful image. So obviously, that's a crappy image. How do I get a better image? Well, take a longer exposure. You get as much. Basically, if you open up the shutter for longer, you collect more light, and as it happens, signal. If you do that, the ratio of signal to noise, how much signal you gain versus noise, goes as a square root of n, which is the number of counts. So basically, what that really means is that the longer you expose, the more photons you really get from the signal from the object, and less compared to the noise. Oh, Tiny Captain has a question. I live in a dark sky area, don't have the money now to buy a telescope, but want to in the future. Can you advise me on which one to buy? Um, so my that is an excellent question. My recommendation is a Dobsonian telescope. A Dobsonian is a type of reflecting telescope that is really just a tube with a mirror at the bottom, a mirror, an eyepiece at the top, and it has a relatively crude mount in that it's not motorized. You just basically physically point it to where you want it to go. The reason why I suggested Dobsonian is it is the best bang for your buck. In astronomy, bigger is better. The larger your telescope, the better you're seeing. The fainter the objects you can see, the crisper the objects are going to be. And so if you look at the aperture size per dollar, a Dobsonian is the best value for your money. And you can get Dobsonians, a small Dobsonian, like a 6-inch Dobsonian, you can get that for a couple $100. The reason why I suggest that is to see if you really want to do this. It's a great way to learn the sky. It's a great way to learn the night sky using star charts. And you can always point it at planets. Planets are fairly easy to find. The moon is very easy to find. And if you really get excited about that, if you get excited and you start learning the sky and you really enjoy it, then I think you can start graduating up to larger telescopes or more expensive telescopes with motorized mounts. What I find is if someone goes immediately to an equatorial mount or goes to a motorized mount, learning curve on that, it can be fairly steep. And so the person quickly loses interest because it's kind of a pain in the ass to deal with it. So that's why I recommend Dobsonian telescopes. Dobsonian. I believe that is the way to describe it. What is going on here? These aren't round. That tells me I have a tracking issue. Why do I have a tracking issue? CellNav. I'm actually not familiar with CellNav. Um, So yeah, you can start to see the larger the hour, the more seconds you have. You can now start to see the spiral arms coming into play. What I'm going to do is I'm going to try to center this up, and so I. So Tiny Captain, if in terms of, I don't know where your celestial navigation is. Ah, okay, okay. Then yeah, I would I would go with the Dobsonian option because for one, if you're really doing celestial navigation with a Sexton, um, then I think you would find it enjoyable to learn the night sky using sky maps, star charts. Um, and so I think a Dobsonian would be an excellent choice for that because with more modern or more expensive telescopes, they have go-to functions, and so you don't have to know the sky with these more sophisticated telescopes because you can literally do what I'm doing and basically just point and shoot once you've got it set up. So yeah, I would if you're interested in that sort of thing, which I get the impression you are, get your hands dirty with the job story. All right, I think that's good. So left goes right. All right, I have to note that because I have to tell people that we're having. Never mind. All right, so 30 seconds. Let's go 60. Just so you know what exposure time I want. I'm just doing this as sort of just to indicate how an image changes when you look at it with different exposure. So at 10 seconds, we saw essentially just the cores of the two galaxies. At 30 seconds, we started to see the two most prominent spiral arms here and here. Oh, by the way, if you want to see another galaxy that I've taken, this was a while ago. Um, that was the Andromeda Galaxy. I took that image a while ago. That is the closest major galaxy to us. It's 2.5, 2.7 million light years away. It is also a spiral galaxy. It looks very similar to what we expect the Milky Way galaxy to look like. All right, now 60. The Not a lot of difference. You got the arms, but not great. I'm going to pump this up to where I think it needs to go, which is 180 seconds. Uh, Jobs are great for visual observations and learning tasks. Yes, I agree. I would not if you're interested in astrophotography, I would not recommend Dobsonian. The base is, unless you have like a 16-inch, the base is not stiff for that to work. Today's stream brought to you by Mellow Yellow. After I'm done with this, after I take this image, what I'm going to do is I'm going to talk about the three filters that I'm going to shoot through it: blue, green, and red. Essentially, if you are up on the lingo or up on the technology, what I'm actually shooting through are the Johnson blue, visual, and red filters. All right, Johnson blue, Johnson V, and Johnson color cousins. what that means is uh, filters are filters. They filter, obviously, as the name implies, they filter out light. So B, for example, Johnson B filter blocks out all the light except for a portion of the light in the blue part of the visual spectrum. Um, there are many different types of filter systems. And what that means is you can have multiple filter systems that look in the blue, but don't look in the same wavelength range as blue. And that you need to know what type of filter it is in order to do real science. You need to, if particularly if you want to compare apples to apples, like comparing a blue to a green image, both of them need to be in the Johnson system in order to basically get anything out of it. What's the word I'm looking for? So that's why Johnson. And the Johnson red is slightly different than the Johnson cousin. I'm not entirely certain why Johnson cousin kind of took over versus the Johnson R, but it's really important, I guess. And so that's 180 seconds. I've got music on in the background. That might be it. So if I'm having audio issues, I'm just gonna get rid of that. So, or I might play it up. Nah, it's great. I will not play with music. Anyway, so 180 seconds, or I can do math, 3 minutes. In 3 minutes' time, we definitely see the spiral arms. On top of that, we can start seeing these little knots, little bright points in the spiral arms. Those are not stars. Those are so that's a star, that's a star, that's a star, but that thing right there is what we refer to as a star forming region or a giant molecular cloud. It appears star like because of the fact that you have stars that are particularly big blue bright stars that are forming in that region. So, typically speaking, if you look at a galaxy, particularly with a telescope of this size, you will not be able to distinguish individual stars. You can just see the overall conglomerate of the glow of it. So, all right. So that's what it looks like in the red or green. I'm also going to do this. I'm actually going to. Yeah, I figured that was the case. I'm using StreamYard, so I figure that overly it's not overly what's the word I'm looking for, sophisticated in terms of audio mixing. So yeah. So this image, which I'm going to save, save. Um, mhm. Oh, that one. Whirlpool. Whirlpool. B180. Really, I should have done 180 just to be apples to apples. But now what I'm doing is I'm shooting I'm imaging the Whirlpool in the red filter. So at around 600 to 700 0.6 to 0.7 nanometers, as opposed to 0.5 to 0.6 nanometers ish. And the reason why I would do, from a scientific point of view, what this not only does it give us pretty pictures, but it also tells us something physical about the object. It traces a different temperature range. So this image is more sensitive to cooler physical phenomenon. So cooler stars, dust, that sort of thing, than the green image is. So what I'm hoping for is those star forming regions are going to look a bit different. Okay, so I'm going to put this onto blue. Let that go while I talk. Yeah, start. Did I start? No, it's moving. Okay. Let's do that. Let's open up Whirlpool. This isn't quite apples to apples because, again, the exposure times are different. But what I want you to see is that these regions, these knots here, actually appear a little bit brighter. That's mainly because of sensitivity. But what I'd like to sort of convince you of is this inner region, particularly this right here. The red filter is more sensitive, like I said, to cooler material or cooler physical phenomenon, like heat light or heat radiation or radiation coming off of dust. And so in the red, we see more of a contribution of the dust inside that galaxy, which is primarily which has a higher proportion in the inter-arm regions than it does anywhere else. So in this inner arm region, you can see that it's brighter than it is over here in the visual. And that's not a consequence of exposure. That's not a consequence of screen stretching or anything like that. That is a consequence of the fact that we are looking at, or we are more sensitive to the dust that is located in that region than we are if we were looking in the green. In the blue, this really isn't really present at all. I'm hoping with the blue image, really what we're going to be able to see is the spiral arms and not much of material in the inter-arm regions. Here, you can also see the stream, the interaction between this spiral galaxy and this remnant galaxy. I don't know what it was beforehand, but this galaxy is eating that galaxy in a process we refer to as galactic cannibalism. And so this material here, this stream is material that is being ripped off this galaxy and going into this one because of the larger amount of mass that is located in this larger galaxy. It has more tidal forces, and it's literally ripping that thing apart. But it's doing so, and it does so on a short astronomical time scale, but not very long in terms of us. I think my blue image is coming up. There we go. So I will freely admit that the blue part of the part of this chip and the telescope itself is not as sensitive to blue as it is to blue light as it is to green light or red light. But I hope you can see, I convince you that really with the spiral arms, you can see these chunks but you really can't see anything here. That pretty much looks like the background sky. There is no glow there from dust, and even the spiral arms you can't see a whole lot. Oh, okay, Peter. I'm going to kill Discord. Quit. Yeah, you can't see the spiral arms as continuous structures. You can really only see these star forming regions that are very blue and very bright. So now this is the part of the program this is the part of the observing process that is not overly exciting. And that is, I am going to set up my exposures. So I've already set up my exposures. Options. Nope. Okay. What this is going to do is, oh, I know why they did that. To make it, all right. 1 second. You have to bear with me. You. Yes, you. Go over here. All right. Blah, blah, blah. Now my ass is getting bigger. What is this thing set? Oh, it's up in the sky for a long time. All right. All right. Yeah, I'm going to do it that way. Because that's going to cut down on, oops. That's going to cut down on the amount of time. So what I'm going to do now is I've set this up. I am going to take 10 exposures in the blue. Each of them is going to be 180 seconds. And then it's going to switch off. Then it's going to switch to the green filter or visual filter. It's going to take another 10 at 180 seconds apiece. And then 120 of them at 10. It's more sensitive. Actually, you know what? Nope. I'm going to do it. I want to make them all the same exposure time. So, yeah. And then I'm going to just go. I'm just going to do it. All right. And this is the, can't remember the dude's name. This is the set it and forget it. It now will, for the next probably 2 hours or so, I just get to sit here and watch it. So, what is the base focal length of the telescope? Excellent question. For those of you who don't know, the focal length is the distance from the mirror, the big primary mirror, through the telescope down to the camera, and where it focuses on the camera. Let's see. I don't have that information off the top of my head, but I can calculate it. Start. Finish. You go away. Oh, hold on. Stop that. No, that's not what I want. Go away. Nope. Office, calc. Hey, all right. So the telescope is an F8. So I don't know why I'm using a spreadsheet to do this. 256 inches. Or Actually, I'm going to do it this way. 256 inches to millimeters. 6,500 millimeters, thereabouts. 6502.4. But honestly, I think it's not quite an F8. But yeah, so basically 6,500 millimeters or an F8. No, don't save. What was I going with? So what that means is, for those of you who don't know, is the F ratio is an indication. It's the focal length of the telescope divided by the aperture of the telescope in the same units. So the focal length of so for example, the focal length of our telescope is 8 times larger than the size of the mirror. One of the things that determines or dictates rather is your field of view. How much of the sky are you going to be looking at using your camera? An f8 is what is known as a slowish telescope. Meaning, but to my point, it means that the field of view is smaller in comparison to, say, an f3 or an f5. Those have wider field of views than an f8. Going back from the beginning, I was talking about open clusters and how they are large extended objects, and they are really hard to image, or they're kind of a pain in the ass to image with our telescope because our field of view is too small in comparison. Yes, IB. So F8 is pretty good for planetary. For us, though, for some reason, I think it's because of our plate scale. Our planetary images are Jupiter, Saturn are just way too small. We need a different camera, I think. Oops. We need a different camera for it. I want to get a CCD that is specifically designed for planetary work, but I haven't worked out what the pixel size has to be for that, or ideally what the pixel size needs to be for that. I know I want to go with ZWO. ZWO makes fantastic planetary cameras. But yeah, so F8, good for planetary type work. Planets, the moon, good for galaxies. Not so good for extended nebula, like really big star-forming regions, or dark nebulae, or open clusters. That you need a wider field of view on the order of a degree or more. So, yes. So CMOS might be better for planetary than CCD. Yes, yeah. We are currently. This camera is technologically old. It's at least 5 years old, possibly approaching 10. And we are getting to the stage where we want to replace it. And when we do, we are getting a CMOS chip as opposed to a CCD. One of the issues that we have also is this USB 3? Is the telescope and the control computer are so far away from each other, we actually have to send the signal through, we have to convert the USB signal to Ethernet and then back again. And I think that is also causing a bit of a delay. Granted, I'm also doing 1x1 binning. I'm imaging over the full chip as opposed to averaging over multiple pixels. So yeah, our download time is like 12 seconds. It's ridiculous. In my opinion, it's too much. It's ridiculous. I could make it shorter by going to 2x2 binning, But yeah, I want the I want the resolution. So so yeah. You guys have any questions? I like, people are posting. Anyone else in the audience has questions? Feel free to ask them, and I will try to respond. I'm gonna look over on Discord. Oh, here we go. Message requests. Oh, we have someone who wants the live stream. Copy. I think this person is from Tartaria. Tiny Captain. Oh, Tiny Captain, apparently you've found the link. So, oh, and IB Hunter, you also have found the link. So, there we go. Let's see. Awakenings. I can't help but I keep getting drawn back to flat Earth stuff. I think it's because I just, I want them to see what this is, what we do for a living, us astronomers. But I'm ignoring my chat. Yes, the image here is going to be much better than a P1000. Actually, let me see if I can pull it up. While we're sitting there doing that, what I can do is desktop for tours. We need the humor of derp, yes. So the images that I'm about to open up, these were taken by students here at George Mason University and put together by students. So as you can see, these are the images that you're seeing here, obviously, are monochrome. They are grayscale. As I mentioned before, this particular image, for example, is only looking at blue light. So it ignores everything else. Now, if you know anything about art, I guess, probably know more than I do. If you have a blue image, a green image, and a red image, you can combine those three and get a true color image. And so what our students have done, is taken images like this in blue, in green, and red, or sometimes in green, red, and H alpha to make a false color image and put it together. So let's look at some of them. Cooling is cool. All right. I don't know what that is. Galaxies. All right. Whee. Let's do. There we go. This is a recent image again with this telescope. These are what our students have done. Amazing. It is. I think the title tells me what. Oops. There we go. Okay, title is over here. So this is a composite of R images that were 90 seconds long, V images that were 120 seconds long, and B images or blue images were also 120 seconds long. So right now I'm doing R of 180, V of 180, B of 180. But you can see this image is, I think, phenomenal. It is the color balance on this is amazing. One of the things that is difficult in astrophotography, particularly in this style of astrophotography, where you're combining the three images, a blue, a green, and a red, is getting that color balance. Because as I said, or sort of alluded to before, the what am I looking? What am I trying to say? The telescope has a different sensitivity to blue light than it does to green light than it does to red light, and so you have to be very careful on how you balance how prominent one image is to the other. And you can see that the stars here are primarily white, which is really the case. But these stars that appear red, those are in fact intrinsically red. But you can see with the galaxy, these beautiful spiral arms, these red or these blue dots. Those are those star forming regions I was talking about. You can kind of see the haziness here, particularly over here. That is the dust that is in the inner arm structure. And then you can also see really pronounced this dark region right here. This is a dust lane inside the galaxy, inside the arm. You can also see dust lanes over here and over here. You can also see that this galaxy is older, primarily because it doesn't have a lot of blue stars. The blue stars have evolved and died into supernovae. And all that's left are these red stars located in there. So, yeah, I love this image. This is, like I said, this is one of our students. He is way better at this than I have, and I've been doing this for a while. Granted, I could put more work into it. Here's an example of a bad, a bad combination. You can see in this case. There is way too much red in this image. The color balance is such that there's too much red. The red image is being prioritized, I guess, more than the green or the blue. But you can still see it's a beautiful, beautiful image in the sense that, it's nice, crisp arms. You can definitely tell there is a color difference between this galaxy and the galaxy above it, or galaxy that it's eating. This is a raw image. This has been scaled a little bit, so the background comes out. But you can see that it's been attacked by a cosmic octopus, or the Great Spaghetti Monster, if you want to go that route. Really, what this are these sucker marks, these rings, are dust particles that are somewhere in the optical system that are being imaged out of focus. And so we need to take a particular type of calibration frame in order to rid ourselves of that one. Let's see, what else we got? This is, I believe, this is the Splinter Galaxy. So this is an excellent learning opportunity. I can go to that one. You can see here, this is a spiral galaxy. Spiral galaxy means that you have a bulge or a central concentration of stars, and then you have spiral arms, sometimes 2, sometimes 4, sometimes many, that appear to be emanating from that bulge and then wind outward into space. That's a spiral galaxy. This is a face-on spiral galaxy, meaning that we're looking down on top of it, in a sense. So we are looking down, we can see the disk in its full glory. That is a spiral galaxy, but edge on. Same kind of galaxy as that one, but instead of looking down onto it, we are looking along the side of it. So we're only seeing the edge of the disk. And this particular galaxy is probably an SC or maybe an SD, meaning that the bulge is not very significant. The bulge is rather small in comparison to the rest of the galaxy. You might be noticing these arcs. That's, I don't know what that's from. That's some kind of noise. I think it's coming from the filter wheel, but I don't know. That's not something we've encountered a whole lot. It's one of those lovely errors that pops up whenever it feels like, with no rhyme or reason to it. This is also very exciting. So I can't remember what what is the cause of spiral galaxies, and how do we know we are in one? That is an excellent question. So I can't give you a very great answer for spiral galaxies, but the cause for a spiral galaxy has to do with how it formed. So if it if it collapsed faster than, what's the word I'm looking for? Basically, if it collapsed rapidly enough, before star formation really took hold, before all of the stars really formed, then you're going to get a disk. Now, the spiral arms itself, and this is the point that I am a little bit ignorant on, well, pretty ignorant on, is there is something causes a density wave to pass through the disk. And so that causes the clouds, the molecular clouds and the stars to compress in certain areas, those are the arms, and then rarefy in those areas between the arms. So it's a density wave that goes through. What causes it? Like I said, I'm not entirely certain. This particular one is this galaxy here, I believe, is NGC 4647. It is the 4,647th object in the new general catalog. That's what that means. This is a spiral galaxy. Hopefully you can kind of see that. This is a nearby elliptical galaxy. You can, again, this is a great example of contrast between the two types of galaxy. You have a spiral, as we've seen, has spiral arms. An elliptical galaxy, because astronomers are oh so creative, looks elliptical. It looks just kind of like a centrally concentrated blob that either can look like a sphere, can look like a rugby ball, or it could look like a cigar. It has various, it is oblong to various degrees, depending on which galaxy you're looking at. But the cool thing about this image is what's being highlighted. That, my friends, is a supernova. That was serendipitously caught by our students. So if you were to look at this object again, if I were to move the telescope to this object and image this again, that white dot would no longer be there. And so this is kind of the rare exception to being able to see individual little stars, individual stars in a white or in a galaxy. When they go supernova, that is when you can see it. Because supernova are the second most energetic phenomenon in the universe. They are, I think, trillions of times more powerful than a megaton bomb. So they release just a sheer massive amount of energy when they pop off. So much so that we can see them at very large distances. And so we just happened to, I don't know if we had gotten word or if the students were just serendipitously looking at this object and we're like, that's new. And then looked into the news and basically saw that that was there. You can also see, again, another faint elliptical galaxy over in this area. And I keep saying again, color balance. The person who put this together, I think it was Owen, the ability to make these stars white and to get, hopefully you can see the bluish color in here, which means there is active star forming region in the spiral galaxies. This is an elliptical galaxy. As I've said, it's red. We often refer to them as red and dead, meaning that there is very little gas in these galaxies anymore, free floating gas in these galaxies anymore. And there is that from that gas that stars form. So there is no active star forming in this galaxy. So when bigger, brighter, bluer stars run through their lives and die in supernova, there's nothing to replace them. So all you have left are the population of long-lived redder stars. So we got that. let me check on this. All right. Hey, Judy. Howdy. And so, for those of you who might be just coming in, this is M51. Better image of it that I was gushing on before is this. Obviously, it's been flipped. And I am taking a sequence of blue images that are each 180 seconds long or 3 minutes long. I'm going to now, later on, I'm going to take, or as this progresses, I'm going to take green images, and then as it progresses, I'm going to take red images and try to come up with something that looks like this. I doubt I will, and I have hope that I might actually be able to stream me doing this because summer is coming and my teaching schedule for summer is backloaded. So I will be teaching summer C. So I will have like a month or two without teaching. So I will have more free time. Anyway, now I'm going through galaxies. Same image, just for rotated for some reason. This is NGC 891. Again, we see basically an edge-on spiral galaxy. I believe this is the cigar galaxy, but I could be wrong about that. And what we have here is this dark lane. This is not a galaxy that's been cut in half from, along the edge. This dark region is very similar to what you see with the Milky Way galaxy. The Milky Way galaxy has these dark regions inside that sort of milky structure. That's because of dust. Dust blocks light very effectively in the optical. It particularly blocks blue light and green light a lot better than it does red light. Or it can just block out all of the light entirely. One of the reasons why JWST is looking in the infrared rather than the optical is because of this. A lot of the science that JWST wants to do requires looking in very dusty regions. Young star forming regions are very dusty. Galaxies can have a lot of dust, as we've seen, and so they want to basically look through it. But if you look in the optical, you get a lot of dust, and you get these lovely dust lanes that go through it. Here's another image, basically that shows you what I was talking about, color balance. So same images, just different ways of processing it, different ways of balancing it out. You can see here that in the background, there's a lot of red over here. Over here, this is a lot of blue, a lot of green. And so what's happening here is that the backgrounds of these, the red images, the backgrounds of the blue images and the green images, they weren't flattened enough. Basically, one half of the sky was brighter than the other half. So you can do things to mitigate that effect. And so one of the ways, and so here, this indicates that, this is the redder area is less prominent, the greener area is less prominent, but it's still not perfect. I mean, these are students, they're still learning. This is a very, very old or very, very small galaxy. It is NGC 6040. It is 564 million light years away. This may be the farthest galaxy we have imaged here at the observatory, or really the object that is furthest away that we've ever looked at. Yeah, you could say that, yes, it is in fact a dustbuster. There was a long time ago. I was in a talk, colloquium, as we call it, or a talk, and this guy was talking about interstellar dust, or the ISM, and he was talking about how when he graduated, his PhD thesis was on dust, and when he graduated, his mother bought him a vacuum cleaner as a celebration. Dust doesn't get a lot of respect in the astronomical community. A lot of our astronomers really think it's really just a nuisance and it's just kind of really, really boring. But there are a subsection of astronomers who really get there, really, really love looking at really, really small grains of sand. So, I don't know. No kink shaming here. So here you can see again, you have a spiral galaxy. What looks to be a spiral. Well, actually, I don't know. It could be spiral or it could just be a tidally distorted elliptical galaxy. But it is 556 million light years away. This here is more than likely a closer elliptical galaxy, but I'm not entirely certain. I couldn't swear to it. But yeah, that is one of the. You can see the pixelization you see here is a much more basically a zoomed in like this, a zoomed in picture. So it's very, very small. Hazard a guess that it's maybe an arc minute or two in full size. As I said before, the actual field of view of our telescope of this camera is 25 arc minutes squared. So we've got that. Oh, this is one of my favorites. This is M101, or the firework galaxy. Again, you can see a lot of this. So this is what we refer to as a flocculent galaxy, not a flatulent galaxy, but a flocculent galaxy spiral, meaning that the spiral arms, for one reason or another, are not really cohesive. They have a lot of breaks in them. They have a lot of kind of irregular structure to them, as opposed to a grand design spiral that has really nice crisp arms. But you can see that this is called the fireworks galaxy because there's a lot of star formation. This is what what astronomers refer to as I just lost the term. Star something region, or starburst galaxy. That's what it is. Starburst galaxy. So this is a starburst galaxy. That what that means is, again, for any or for a couple different reasons, something happened that caused star formation to increase. More than likely, the most likely candidate of that to do that is either a merger, a galaxy. This galaxy slammed into another galaxy at some time in the distant past, and that caused the dust to go flying all over the place and basically collide in with each other. And as the cloud collides with another cloud, it gets denser, pop off star forming stuff. Or supernova can do it in a more localized region. Supernova can also cause the stars to collapse, or the clouds to get denser, and for stars to form. But again, this is a pretty good color balance. You can see that we're still having issues with flattening out the background. We have too much red over here, too much green over there. But it's awesome. This red is real in the sense that these are pockets of concentrated hydrogen gas. So these molecular clouds are primarily composed of molecular hydrogen. So the blue areas inside these clouds, those are the stars. The red areas are the surrounding hydrogen gas that is being illuminated by those stars. You can kind of think of it as a fluorescent light bulb. The gas is fluorescing around it, is being excited. The gas is being excited and shedding off its own light because of the star in the middle of it. This is M100, another spiral galaxy. Again, it looks similar to to this one, M50, the Whirlpool galaxy, but as you can see, it's different because there's it's not eating anything. Here you can see a lot of background galaxies. So if you've been looking at the JWST images, one of the things that just wowed astronomers is the fact that, particularly those deep sky images, you find background galaxies everywhere. They're just the universe is composed of trillions upon trillions of galaxies, And even here, we can get images, as you can see. This is a 45-minute composite image of red, blue, and green, meaning that we observe this object for 45 minutes. And you can see this is an elliptical galaxy, background elliptical galaxy. There's another one. There's one. That is probably one. That is one. That may be one. So definitely, even here, we can get images where you get a background. You basically these galaxies pop out that we're not even trying to look at. This is M82. Is this a cigar galaxy? I can't keep this thing straight. M82. Again, this is definitely a starburst galaxy. This really doesn't do it credit or do it justice. The background really needs to. The scaling on this is a little bit bad. But what am I thinking of? But this is definitely a starburst galaxy. If you look at the Hubble version of this, you actually get to see these outflows due to supernova activity coming off perpendicular to the disk. Have we seen gravitational lensing effects? I have not. I do not believe that we have done that. And actually, that has occurred to me recently that I should try to find some. Find some objects that have some where gravitational lensing has been seen and see if I can image it here at the observatory. The problem is what I suspect is that those things that I can find that have gravitational lensing, those are very distant objects. And so, well, at the very least, the objects being lensed are very distant, which means they're all probably very faint, which means our telescope might have a hard time imaging them. But I will, but I am meaning to give it a shot. Oh, this is talking about color balance. This is this galaxy. And so here, in this case, the images were much better. The night was probably better. The images were of better quality. And you can see this definite red images. And you can see the red popping out here. And this is basically gas that is been blown out from this galaxy due to intense supernova activity. Did Bob go live? I probably missed it because I was teaching. For some reason, I don't get notifications on his streams, so I haven't been able to pop in on him and say boo. Believe that is the same galaxy. Again, images not great. M81. This is a case where we're not looking at it edge on. We're not looking at it face on. We're looking at it at an angle. That's why the galaxy looks a little bit oblong. But if you were to go over here, over to kind of the right, if you move the Enterprise over here and look down, you would see it more face on. If you move the Enterprise over here and look this way, you get edge on. Again, this is a beautiful image. We have diffraction spikes coming off. That means these stars are being overly saturated. You can see the dust in here really, really well. Not a lot of star forming in these arms, so this is probably a much older galaxy than the rest. But you can see again these dust lanes. This is beautiful. This is just a fantastic image. And I have to say, these are all student none of these are mine. These are all taken by our students here at our observatory, our tour guides, and also our astronomy club. Here's M66. Not the best image, but what's interesting about it is that this is what we refer to as a barred spiral galaxy. You have so if we go back, this is a spiral galaxy. You have the bulge, the central concentration of stars, and then emanating off of it, you have these nice spiral arms coming off. And you could get 1, 2, 3, or excuse me, you get 2, 4, or a few different spiral arms coming off of it. This, you can see there's an elongation here. Now, some galaxies are actually barred spirals. Oh, and this goes to the question that Indy asked that I did not answer. Is that so we have the barred spiral, like said. Again, I don't really understand how that bar gets set up, or what is the physical mechanism for why that bar exists in some galaxies and not others. But our Milky Way galaxy is believed to be a barred spiral. That's a fairly recent, last 20, 30 years of study. How do we know that? How do we know that we have spiral arms? Distances. So if you plot the distances of stars over space of the galaxy, what you'll notice is that there are regions. So you have a whole lot of stars that are in this sort of, this sort of distance, plus or minus 50 light years. Then you have a big gap, or plus or minus 100 light years, I guess. Then you have a big gap where you don't see a lot of stars at a particular distance, and then you see yet another set of stars that are basically in the same distance area, given plus or minus 100 light years or so. That's really just a made-up number, but hopefully the idea is you see a whole lot of stars at one particular distance. There's a gap where you don't see really any at all, and then you see stars that are at a distance that's further out. And if you do that over 180 degrees, you can map out the stars in a three-dimensional grid and you can get an image of what the approximate image of what the galaxy actually looks like. And from that, you can also see the bar. The reason why the bar was a relatively recent discovery was because the bar is located near the galactic center. There's a lot of dust in the galactic center, and so it's really hard to see, or was really hard to see with any kind of resolution through that dust. So things like Hipparchus, for example, was an optical mission, so it didn't get a whole lot of distance measurements in the inner part of the galaxy. M109. I don't think I've ever looked at M109. Oh, there's M51 again. And that's it. That's it for the galaxies. All right, we're now into the green. So here's the green image of the M51, the Whirlpool galaxy. Let me check something real quick. Oh, we're still pretty high up in the sky. We are an air mass of 1.03, so it's not even at the meridian yet. Air mass is a estimate of how much atmosphere you're looking through. So if you're looking straight up, dead straight up, that is an air mass of 1. You were looking through 1 atmosphere, essentially. And as you drop to the horizon, you're looking through more and more of the atmosphere. And so, like 1.03 means that you're slightly off center from zenith. If you get down to about 1.5, you are, I believe, at 45 degrees. And then it just gets larger from there. And astronomers really want, even from making pretty pictures from science data, you want it to be at a low air mass. The higher the air mass, the blurrier the images, the more error that's going to creep into your data. So yeah, we're still good. Hopefully, though, I haven't checked the weather. Hopefully, the weather is cooperating. Ooh, we got some kind of smudge. Smudgy smudge. All right. Where was I going with this? All right. Moon. Yeah, there we go. that gives you a sense of our field of view. So full moon, or pretty close to a full moon. So like I said, 25 arc minutes. The full moon is 30 arc minutes in size. So we can almost capture the entire full moon in our images. Here is the moon close to first quarter. So again, you can see these nice crater features. You can see the mare. I think this is Mare Imbrium. I think. Pretty sure this is Tycho. Might be Copernicus. I honestly don't know my selenography all that well, or lunar geography. There's a particular region that I know dead on because I used to do astronomy labs that localized on that area. Basically, it was a great area for teaching students how to determine the heights and depths of craters using Galileo's old method. And that's just a really bad scaled picture of the moon. I don't even know why that's there. Nebulae. Oh, yeah, good stuff. This is the Bubble Nebula. Again, astronomers are really not all that creative, so you can probably guess why this is called the Bubble Nebula. A lot of these nebulae are planetary nebulae, meaning that these are clouds of gas that once belonged to a low-mass star, a star very similar to our sun, and near the end stages of its life, the star pulsates violently, and it blows off these outer layers. It's not a supernova by any stretch. It's far lower in energy. It's a far less energetic event. There really isn't an explosion in any way. It just shakes itself apart, and that gas expands out into the cosmos, leaving behind a white dwarf. So that's the Bubble Nebula. Yeah. Oh, starting to get a little pixelated. Go there. This is another image of the Bubble Nebula, but again, the color balance is a little bit messed up. Also, I think the exposure times were not nearly as long as the ones here. So this more than likely has more data to it, longer exposures than that one does. But you can see, you have these darker regions here as opposed to these brighter regions over there. That is astrophysical in nature. That is not an imaging artifact. That is basically a little bit more dust in this area blocking out the background sky brightness. So those are what we would refer to as dark nebulae, dark nebulae. This is a really bad image, a really red image of the Crab Nebula. This is a supernova remnant. This was, I think, the first supernova remnant ever discovered. It is M1. It is the first object that Messier decided to write down. It is a star that we believe corresponds to an explosion seen by the Chinese in 1040 some odd, I believe. And it is explode. So this star exploded in a supernova, and this star exploded in a supernova within our own galaxy, and it is awesome. Let's see if we have a better picture of it. There we go. Not great, but still better. And so you get these. Again, this is hydrogen gas that is being excited, probably due to the compression of the gas as it shockwaves as the supernova goes out. What's really fun about the Crab Nebula is that supernova remnants are rare because they are very short-lived. We're talking on the scale of tens to maybe hundreds of thousands of years for it to be cohesive enough, to be bright enough for us to be able to see it. And what's really so we're talking about gas that is being expelled out into the universe at rates of hundreds of kilometers per second, not per hour, per second. And so if you go back to the old Palomar images of 1950 and you go to images today, you can literally see it expanding. It's not much, but it is noticeable. You don't need a specialized tool. You can look at it and be like, yep, it's bigger today than it was in 1950. It is one of the few things in astronomy that I can point to where you can see a astrophysical change over any kind of time scale. I mean, obviously planets move around, that sort of thing. But when you're talking about, pulsating stars or stars evolving, galaxies colliding, eating each other up, a lot of that is on timescales of millions or billions of years. This is one of the few examples where we have enough data, and this event or this phenomenon changes at such a rapid rate, astronomically speaking, that you can see it. You can see it getting bigger. It's just awesome. It's just awesome. Then you have, this is the dumbbell. This was number 3 on my list of image targets. Now, 4th. So it was Whirlpool. My second was Sombrero. Third was Orion. 4th was dumbbell. And then I don't remember after that. This is a planetary nebula. So somewhere in here is a white dwarf. That is not the white dwarf. Somewhere in here is a white dwarf. It has expelled its outer layers, and it has formed a nebula. Here is I think, a better picture of it. Ta-da! Color balance is a little bad. Most images I've seen, this is probably more true color. The Dumbbell Nebula is in a region of space that has a higher population of redder field stars for some reason, which I haven't really looked into. Yes, they do have to rename these things. And so this is way too blue. This is way too green, really. This is not what you would see from the porthole of or view screen of the Enterprise. This is closer to it. It's also a much better. This is an example of either better seeing or better focus. You can see that these stars are a little bit more oblong or a little bit more blown out than those. And so you can see finer detail in the center region than you can here. But one thing I want to point out is we go all the way back to the Bubble Nebula. No two planetary nebulae really look alike. And the main reason for that, there are 2 reasons for that. And that is, well, maybe one. Orientation. So you have a star, it blows off its outer layer. So depending on where that orientation is, the rotation axis, that's going to dictate how the structure to first order of how this gas gets blown out. Whether or not it's going to look like a dumbbell, whether or not it's going to look like a circle or a sphere. The other thing, and this is probably the more at later stages, this is the larger influence, is magnetic fields. The magnetic field of the star gets basically brought out, gets extended out and brought along with this gas, and it's going to affect the structure. And so in this case, yeah, it kind of looks like an apple. And so no 2 planetary nebulae look the same. They're roughly biconal. Biconal, is that a word? It is now. In that you have these cones which come off from the north that align with the northern magnetic pole and southern magnetic poles. Fossil foot. This is a new one on me. I've never seen the fossil foot, so I have no idea what that is. An emission nebula, more likely. I do know what that is. That is the Horsehead. The Horsehead is close to the Orion Nebula. So again, you have a region of space where the gas is being illuminated by some star down here, and this Horsehead structure is again dust. So you have dust that, from our perspective, is clumped to look like a horse head. So really cool. I like it. The Lagoon Nebula. Yeah, this is another. I believe this is actually a open cluster that is far away, so it's more tightly constrained. And again, another emission nebula. You can see the dust lanes through here, really pretty. Color balance is, This is also, you might notice, it's pretty pixelated. Again, this is probably because this is zoomed in. It's a fraction of the image. So the Lagoon Nebula is more than likely a very small object. Oh, this is the Little Dumbbell, the Godfather Nebula. I don't know if there's a Godfather Nebula. This is the Little Dumbbell, which is little. And I don't know why it's really called a Little Dumbbell. To me, it kind of looks like a butterfly. But again, another planetary nebula. This is grayscale. I don't know which filter it's in. The Ring. The Ring Nebula. Oh, I forgot. The Ring Nebula. Yeah. That was fourth. Dumbbell was fifth. So the Ring Nebula is a planetary nebula. Again, this is where you're looking down the throat of that cone, of one of the cones, whereas with the dumbbell, you're looking at the side. And so you see both cones. Here, you're looking down the throat, or basically along one of the poles. Yeah, all right, now I got you. And you see these lovely colors. And again, these colors are there because they indicate different temperature regions. As you might expect, the gas that is closest to the star is hotter, so it's bluer. That gas is going to radiate bluer. And then the gas over here that is farther away, that is colder gas, it's going to radiate in the red. That also tells us a little bit about the chemical composition. Green corresponds to a lot of oxygen emission. The red corresponds mainly to hydrogen emission. So it tells us something about, if you were to analyze this data properly, this is where this is the evidence that we have to understand how this came off. And we know there's oxygen here, so there had to be a significant amount of oxygen in the star before this event happened for that oxygen to be in such an abundance in this image afterward. So that's essentially, if you wonder why we know that there's a lot of hydrogen or oxygen or whatever, it's images like this that allow us to do that. Also spectroscopy, but we don't do spectroscopy here yet. It's one of my goals. Oh, ring. More ring. Oh, Pillars of Creation. This is where we are trying to compete with Hubble. So again, one of the sort of prototypical, one of the most iconic Hubble images is the Pillars of Creation in the Eagle Nebula. Obviously, it's Hubble. Way better than our telescope because it's in space. And so its field of view is also smaller than ours. So you get basically a really close-in view of this stuff. So I highly recommend you Google the Pillars of Creation, and you will see basically 3 cloud-like fingers going up that are dark. That's basically what these are. 1, 2, 3. It is called the Eagle Nebula because, as you can see, here's one wing, I guess. There's a tail. There's another wing. Yeah, Eagle Nebula. There. So we have a much better, and this is another, as the name would imply, Pillars of Creation. This is a star-forming region where you have these bright stars in the center. Those are most likely the stars that formed first or very close to being first. And this, and the light from these stars, and probably a couple out here, is what's illuminating this gas. And so if these stars were not here, we would not be able to see this gas at all. It wouldn't be excited. It wouldn't shut off its own light. So we wouldn't be able to see that at all. So it's thankfully, because these things are so bright and powerful, we actually get to see the entire, well, almost the entire cloud structure that goes into these star forming regions. It helps us determine just how massive these things are, how much, well, literally how massive they are, how much mass there is, how big they are in extent. I am going to make this a word. It tells us how radiusive, how large the radius is. So I'm going to make that a word. It tells us how radiusive it is, things of that nature. So compare that to Hubble, and you get an idea of what our telescope looks like in comparison to Hubble. There we go. Yeah, we've seen that one before. This is NGC 7139, another planetary nebula. Our student Owen really wanted to have a collection of planetary nebulae. He really liked looking at planetary nebulae, so he really wanted a collection of them. But as he found out, planetary nebulae are few and far between, or at least ones that we can see are few and far between. The primary reason for that is while planetary nebulae are longer lived than supernova remnants because the expansion is not nearly as fast, it's still, astronomically speaking, a fairly quick event, which means chances are you're not going to see one because chances are it's just not the right time. So yeah, they're hard to find, at least far to image in our with our telescope. And here again, they are. Oh, and the other reason is planetary nebulae are not very big. They're certainly not like parsecs in size or light years in size. So they all also tend to be small in angular resolution. This is the Orion Nebula. This is not a great image of the Orion Nebula. Please tell me we have a better one. We do. Number 3 on my imaging list, not taken by me. Here, I love this. Again, the color isn't great. It's too blue or too violet, but you really can see the batwing structure of the Orion Nebula. The Orion Nebula is the only nebula that you can see naked eye, kind of, sort of ish. If you look, so you have the 3 stars in Orion's belt. Take the center star and go down or towards the horizon, you'll see 3 stars that correspond to his sword. And if you look at the middle star, you can see that it's fuzzy. Hopefully you can see that it's fuzzy. If you have good vision, the sky is dark enough. You can see that there's a little bit of fuzziness around it. What you're seeing, that fuzziness, is this nebula. That star that you're seeing is, in fact, these stars in the center, which are called the trapezium. You can see it here. So these 4 stars are known as the trapezium because they kind of make a trapezoid, I guess. Again, it is these 4 stars that formed first, or they were one of the first forming stars, and it's the energy from these stars that is lighting up this entire structure. And this structure is parsecs in size, or 3 light years in size. So this is a very large complex, or very radiusive complex, and very hard to image. It's a very difficult image to take, particularly in the way that if you're not going to cheat with a DSLR or anything like that, it is a very hard object to image because of the contrast or the dynamic range of the thing. You have these really, really bright stars that are very easy to saturate. If you have any kind of long exposure, you're basically going to reach the brightness limit of your camera. But you're not going to get really a whole lot of this faint background. Or you can take a long exposure, saturate the hell out of the center, blow it out completely, and then you get this nice. You can start seeing the outer structure. I have seen, there is a technique which I've seen but I never learned, where you can basically composite um, this kind of image with that kind of image, and that way you can see both. You can get fine detail in the center of the trapezium or the center of the nebula, and you can also see the or the bat wing structures. Here is another. This is basically another part of the star forming region that is being lit up by this particular star. So more than likely, there is. I haven't looked at the in the radio. This would give you a better feel of how much hydrogen is actually here. But I suspect there is still a good amount of molecular hydrogen over here that's just not lit up because it's too far from this star and it's too far from these stars to really be lit up. Initial objects for solar roots would catch the light echoes from a variable star. That would be an interesting project. Huh. I'll have to see whether or not I can find an object where that's feasible with our telescope. Thank you, ID. More. The Owl Nebula. Yeah, you got me. I guess that's the eye, the two eyes, maybe the nose. I guess this would just be the head of the owl. I have no idea. That is also, as you might expect, a planetary. Bring Thor's helmet. Looks kind of like the bubble to me, but yeah, there you go. Again, a little bit too red for my balance, but yeah. Again, emphasize student done. This is Owen's pride and joy. This is the Trithyiid Nebula. This is an emission nebula. This is not a star forming region. Again, the emission nebula is where you have a bright star like this, or a bright star down here, which is illuminating the galaxy, illuminating the gas and part of it. You also have a dark nebula. You have dark nebula over here. So these regions that are darker, that is because, again, dust. And you have a reflection nebula. And what a reflection nebula means is that instead of the light being emitted, the light is literally bouncing off the gas. I think that's what this is over here. So it's one of the few objects where you have three different types of nebulae superimposed on each other. You have an emission nebula, which is, like I said, the bright gas that you see here. You have dark nebula, which is due to the presence of dust. And then you have a reflection nebula, which I believe is what this feature right here looks like. Yeah, the colors are real. This is a true color image. It's an RVB. The color balance is pretty good. It's probably as best as we're going to get here. And so that is definitively a blue star. That is definitively a red star, a red supergiant probably. And the colors correspond to a different composition. So the red here is a lot of hydrogen gas. The blue here, I'm going to have to punt. I'm not entirely certain what the blue, what the chemical species down here is. But the red is certainly, this is H alpha. This is it's basically just, it's textbook hydrogen emission. And that's it for that. And I believe we are on to the red images. Nope. Ha! Yes, we are starting our red series of 130. So I'm going to be taking 10 more images of the Milky Way, the Whirlpool galaxy, and yeah, that's it. And then I will go on to, depending on the time and depending on the weather, I can go on to another object. I can take requests. If you have any objects that you would really like me to try to image, please let me know in the chat, and I will try to image them, assuming they're available. Just keep in mind, 25 arc minutes squared. So if you want me to look at something that is 1 arc minute in size, it's not going to come out so well. So, planets. This is what I was talking about. I think it was IB. Here is. This is one of the better Jupiters that we can, Jupiter images that Owen has taken. And this isn't actually our CCD camera. This is from the webcam. Or no. This isn't webcam. This is from his own planetary camera, the ZTO. It was attached to the 32-inch, but we don't own it. That camera is Owen's. But this is the type of image that we can get. You can see the banding. For those of you who saw my lecture today, the nice banding patterns across it, the zones and the belts. You might be noticing a conspicuous absence of something, and that is the Great Red Spot. And that is because the Great Red Spot is on the other side of the planet. This is one of the ways that we know that Jupiter is a sphere is that you can literally watch it. I've done it before. You can watch the Great Red Spot go from one side to the other. The Jupiter's rotational period is around 11 hours. And so if you observe it over 2 or 3 hours, you can definitively see it move. You can see it foreshorten. You can see it pop in. You can see it kind of get broader as the foreshortening becomes less and less. Then it foreshortens again and then it disappears. Only happens on a sphere. Jupiter, this is the actual image. So this is a close-up image. This is actual image. This is an extreme close-up, pixelated as hell. So what he did was he took, in this case, what I'm doing here with the Whirlpool Galaxy is I'm doing what is known as track and stack. I am taking a whole lot of images. Well, in this case, 10 blue, 10 red, 10 green, and I'm going to take those images. I'm going to stack all the red images on top of each other, all the green images on top of each other, all the blue images on top of each other, to try to bring out the detail of the fainter stuff. And then I'm going to make a 3-color image. Here, this is a color camera, so there is no filter here. And what he did was he took, 50 or 60 very, very short exposures and combined them. The reason why you do that with with planets rather than galaxies like this, because as I mentioned before, the atmosphere causes things to blur quite a bit, and it does so fairly quickly. So for galaxies and things of that nature, your resolution is such that there isn't a lot of fine detail that you're going to be missing out on. With planets, those bands are pretty small in angular size. So a rapidly moving atmosphere really causes them to blur out. So you want as quick an exposure as possible so that blurring effect is minimized or mitigated. And then you can stack them on top of each other to bring out the brightness and the colors. This is again Owen with his camera. These are the images that we've. These are the planets that we can see. You have Mars over here, probably at a moment of conjunction. You can see surface features on it. I'm very impressed with this because I've looked at Mars through our eyepiece, and yeah, it's really not that impressive. It's just basically a peachish little dot. Here, hey, we got the Orion Nebula, or not Orion Nebula. We got the Great Red Spot. He managed to capture the Great Red Spot. This is more than likely Io. This is more than likely Io, one of the Galilean moons. Here's Saturn. I frequently get told when we look at when people look through a telescope, particularly a large telescope, when they look at Saturn, they're like, that's not Saturn. That's a sticker. You just slapped a sticker on the end of the telescope. I frequently get that. Here is Uranus, and here is Neptune. Again, if I think I mentioned this during my lecture today, they're really far away. And they're not all that impressive through a telescope, even with our telescope. They're just too small to see really anything. This is one of the reasons why our information on Uranus and Neptune is not nearly as detailed as our information on Jupiter and Saturn, because they are really far away, and we haven't really, and as far as I know, the only probe that has probed Uranus is in fact Voyager 2. And yes, that joke is never going to get old. But I love this composite. This is obviously a composite image of 5 different pictures. You would not see this in the night sky. This is not a syzygy, whatever it is. Pluto haze. This has got, I don't know what this is doing here. We didn't take this image. There's no way that we took this of Pluto. I don't know what this is. It says Pluto haze, but I don't really believe that. Saturn, taken through our telescope using our camera. So this camera that I'm using now, this is what Saturn looks like through it. Very difficult to get a good image of it because with our camera, the shutter speed is such that you basically blow it out, you saturate it. And this is actually what it looks like when it's not zoomed in. So this is a full screen, 25 by 25. So again, I think it was IB who was asking about the F ratio. This is how big Saturn's going to look with our camera. Like I said, I really want to be able to get a camera with suitable pixel scale, or plate scale, such that we can actually get good images. Because we do have an F8. Uranus? Yeah, Uranus. Yay! I meant to go back on this. So this is an image that I took. It's a raw image. You can see that there's dust donuts or octopus attacks. And I really wanted to come back and take another image of this. So one of these two, I think it's that one, as opposed to that faint one. That's Pluto. That's Pluto. I checked. I looked at the star. So I looked at the star map of this region of the sky. I basically compared, all right, that dot corresponds to that star. That dot corresponds to that star. That dot is nowhere in the star field. So that means that is Pluto. And what I really wanted to do was I wanted to come back a couple days later, because Pluto moves very slowly because it's so far out. I wanted to come back a couple days later, take another image, and basically be able to blink the two and ask the question, which one of these is Pluto? Because while Pluto moves very slowly, it moves faster than the background field of stars, and you would see it move. That's actually how Clyde Tombaugh found it. He looked at star fields like this that were taken at with some interval of time between them, and he just kept manually flipping them back and forth. He looked at this. There was this contraption where you had these set of binoculars, and there was a flip mirror that allowed him to look at one plate, and then you can flip that mirror and look at the other plate. And these were photographic plates. These were not digital images. These are photographic plates. And he would just sit there, flip, 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 flip. And you look to see if there were any changes. There were any of those dots moved with respect to one to the other. He looked through tens of thousands of plates to find and he found Pluto. I don't think he was looking for it. I don't know what he was looking for, but he wasn't looking for Pluto, but he found it. And yet, even still, he voted to demote it. He failed me, Clyde. Failed me. So yeah. So we have looked. I do have an image of Pluto from our telescope. As impressive as it is. Pluto's really far away. It's really fun. All right, planets. Stars. One of our students really likes looking at stars. Oh no, these are globular clusters. So globular clusters, not a really great picture. Aha! This is M13, the great cluster in Hercules. I could look at this if it's up right now, but you can see it. A globular cluster. Globular clusters are the first cohesive structures in galaxy formation. They formed first. They are the oldest cohesive structures in the galaxy. So they are tens of billions of years old, composed of hundreds of thousands, if not millions. In this case, this cluster, I think, is composed of a little bit over 1 million stars. And again, there's a lovely demonstration of gravity in that you have gravity is distance dependent. And so what you would expect is if you have these stars that are gravitationally bound, gravity is going to cause them to become denser in the center and then more rarefied as you go out because the influence of gravity decreases with distance. And so you have what is known as a centrally concentrated object, where you have a much denser region of stars in the center, and then it just kind of the density drops off as you go further and further out. And they're called globular clusters because, well, they're globular. They're roundishy in shape. Again, as you would expect under gravity. This is another image of M13. The color balance is a little better in my opinion. There it is. So this is a bit too goldeny, a little bit too red. This is probably a little bit too blue, to be honest with you. These are also really hard to image well. It's the same effect with the Orion Nebula in that you don't really saturate. You're not going to saturate a globular cluster. They're just too far away. They're too faint, unless you stare at it for hours. But you can get it bright enough that the inner region stars, they're so close together that the angular resolution of your stars gets blobbed out, technical term, and it just kind of the center gets mushy or just gets to become a blob like here. This is a good example. This is M92. And so it becomes a balance between getting a whole, just getting going faint, going long exposures where you lose the center and gain these little dots, these little fainter stars in the outer regions, or doing a short exposure, a lot of short exposures, and trying to keep the individual stars in the center, but still try to tease out these stars further out. So here is M13 cropped. Again, you can see so this is probably very quick. The color balance is all over the place, but very, very quick exposures, rapidly put on top of each other. You can see that there are not a lot of faint stars out here. So we're not catching out these stars that you see here are probably what we call field stars. They're just stars either in the background or in the foreground. They're probably not associated with the globular cluster, but you can see this is a great illustration of, I say that this is composed of hundreds of thousands of stars, but if you look at something like that, you're like, okay, I kind of see maybe a few hundred. But if you can really look at the interior, you can see all of these little dots. And that's nowhere even close to the number of individual stars. It does give you a great example of just how dense these stars are. So another thing that I like to think of, globular clusters are one of my favoriteest things to look at and to think about. Think about all stars. We have enough data at this point that from a statistical standpoint, we are confident in saying that every star in the night sky either has or has had a planet going around them. including these. And so I just try to imagine myself on a planet around a star that is near, just how bright the fucking star of the sky has to be. I mean, because you have these stars that are, the closest star to us is 4 light years, and it's a southern hemisphere star, so I have no idea of what it would look like in the night sky, how bright it is in the night sky. But here, these are stars that are far closer than 4 light years, and so I can't imagine what the sky must be filled with stars, like thousands upon thousands of stars, and I don't know what the night would look like on one of those planets. It's it thrills me to think about what it would be like to exist on one of those stars and one of those planets in the very interior of a globular cluster. Probably wouldn't live very long because you're probably getting irradiated like no one's business, but it would be a very fun or very interesting life, even though you probably die horribly and in a lot of pain, but it might be worth it. M56, this is another globular, but it is real faint, really far away. And yeah, that's all our globulars. Let's see, what else do we have? Oh, the sun. We also have a solar telescope at our observatory, and so we can look at the sun. Here is, I think, a video. This is when they were first trying to use learning how to use this video camera. So this is live. Well, at the time it was live. I'm going to loop it. And so what they're doing is that they're, again, this is a contrast issue. When you try to get the fainter or the surface of the sun to get those nice granulation, you'll lose out on the edge, these prominences that are on the edge of it. I have not read Nightfall. I really do need to read Nightfall. It's been recommended to me a lot of times. So these are all prominences. These are magnetic features, basically gas that is condensing in the chromosphere due to magnetic field lines that are floating above the solar surface, and it causes the material to rain down. Is this the same video? I think it's the same video. Here's another video. Like I said, they were just learning how to use this thing. So apparently it was not very steady. But yeah, you can see there's a prominence over there. And another prominence. And there's another one over here. I think this is on the same day. Here's a sunspot taken with our this is the telescope that we have is it's not a Coronado. It's very similar to a Coronado, and it's 150 millimeters in aperture. It's a refracting telescope, so it looks like a prototypical telescope. Here's a color image of where we took it with. We actually, I don't know what they took this with. I think this is with the planetary camera, Owen's planetary camera. You can see sunspots. You can see the surface of the sun is granulated or malted colors. The brighter regions are gas pockets that are coming up. The dark regions are gas pockets that are colder, that are falling into the sun. You can see that one of the first indications that sunspots are magnetic are these filaments that you can see here in the, particularly in the penumbral region. They're very much like iron filings. They map out the magnetic field distribution in that area. Here's another one. Kind of a, I don't know what that is. Dark spot. Yeah, I have no idea what that is. That is prominence. These aren't really great. Yeah, those must be sunspots, but the angular resolution kind of sucks. I don't know, maybe scaling. So yeah, these are probably sunspot groups. If I had to make a wild guess. There's another one. There's another one. Better. So this is taken through a different filter. I believe. I need to ask Jonathan about this, where these come from. So and so last one, comets. This is Comet Leonard. Owen took this. The colors are bad, but you can see this is the coma. So you have the nucleus of the comet. That's essentially the comet proper. That is the ball of ice and dust, which is flying through space. Then as it gets closer to the sun, it's going to heat up, causing that ice, which is ice to sublimate, primarily water ice to sublimate, which creates the coma surrounding it. And then as it gets closer, it's going to form the famous tail of a comet. In this case, we're only seeing the ion tail. So the ion tail is very linear, very straight. And what this tail is composed of positive ions that have sublimated off of the nucleus that essentially get trapped or interact with the solar wind, which is also ionized, and they electrostatically interact with each other, and it basically drags pushes the material outward in a very straight line. And if you were to extend outward and extend this line, this points directly at the sun, because the solar wind is essentially a radial phenomenon. It comes from the sun and goes out in every direction in straight lines. This is a black and white version of that same comet. Now, the comets the cometary tails that you're probably most familiar with are what we call the dust tail. And that is caused by by radiation pressure. So there is a lot of dust and particulates in that comet that when it sublimates, it kind of takes that material along with it, releases it out into space. And then light actually has pressure. It actually it exerts a pressure on things. These things are so small and so light that pressure is significant enough that it will blow out the dust. And so the dust tail more accurately determines or more accurately shows where that comet came from. It's not an exact match, but it's close. So yeah, and I think I have been talking for 2 hours nonstop. So I'm going to not talk for a second. Or I'm going to try to. I don't like silence. Silence is bad, man. So y'all have any questions? Y'all still out there? Check Discord there for a second. Oh, IB, you've joined my Discord. Awesome. Dun-dun-dun. So we are. I am imaging the ninth image. Imaging the ninth. How do I take calibration frames? All right. So the 3 frames that I take are typically darks, biases, and flats. Bias, basically, so the camera, because quantum mechanics is a thing, the 0 point of each pixel is not 0. It is going to be plus or minus a few. And so, I keep saying and so. In order for the computer not to get confused and throw up, basically throw errors, what camera manufacturers do is they add a pedestal level. They add about, in this case, it's roughly around 1,000 counts to the to each pixel artificially. So when it reads out the 0 point, if it were if it were a perfect pixel, it would read 1,000. So it would be 0 plus the 1,000 they have added. And that way, when you read it out, certain pixels can be, the negative pixels would be lower than 1,000, and positive pixels can be higher. It's really just readout noise. That tells you what the essentially the quantum efficiency that tells you exactly what the 0 points of all the pixels are, which is not the same for all cameras, and it varies. Then you have dark current. So cameras are stupid. Cameras detect all light in a given wavelength range. That light can come from the Whirlpool galaxy, or that light can come from the camera itself. And so a dark current is, so for instance, with bias, just to say, a bias is just an instantaneous readout or instantaneous download of the chip. So it doesn't expose, it doesn't open the shutter, it just reads out what the camera says. Dark current, in order to get a dark frame, you hey Jonathan, what's the word I'm looking for? Dark frame is you expose the camera for a certain amount of time. Now, if you don't want you don't want to deal with biases, you typically take dark frames that are of the same length as your science frame. So in this case, this image is 180 seconds. If I didn't want to worry about biases, I would take a dark frame of 180 seconds because the bias is basically built in. But if I want to try to reduce the amount of error, adding those or subtracting those two images I would actually take, and this is what I typically do, is take a dark current or a dark frame that is 3 times longer and then scale it down. But the question was, how do I take it? So I just basically just tell it to take an exposure without opening the shutter for X amount of seconds. The signal that I gain from that is the amount of light that is radiating off the camera. And so what I can do is I can subtract that light. That is called dark current. And I can subtract that light off of any science images that I've taken. Then flats, which is the black magic of astronomy, of astrophotography. Well, really astronomy. And I'll show you, if you're around long enough, I can show you how that's done. What we do here is we do dome flats. So we take a light, theoretically it's white light, so it's even across the spectrum, and we shine it on the dome. We point the telescope at that place, and we just expose for a certain amount of time where, for me, I like 2/3 well depth. What that means is that the number of counts that an individual pixel can hold ranges from 0 to 65,535. That is what's the well depth number of counts. I like 2/3, but my director likes half. In any event, you expose, so you get a lot of signal. Basically, you image the hell out of that dome. What that does is it gives you a map of the quantum efficiency or a map of the brightness efficiency across the field. It will get rid of the dust donuts, and it should get rid of any background gradient that may be present due to the fact that certain pixels over here are more sensitive than certain pixels over here. So given a set amount of light, you're going to get more counts with the more sensitive pixels than you get with the other ones. And so that's how we do it. All right. That is it for that. All right. Does anyone have any requests? I think the weather is cooperating-ish, although this is getting really kind of soupy. Yeah, this focus kind of sucks. I don't know how good these images are going to be. Yeah, those freaking dust donuts. Hell, hell, man. All right, I'm going to knock the focus down to. So I think the sky is getting worse. I don't know. Who knows? Anybody have any requests? And I will sit back and not talk for a bit. That's what's up. Oh. Hmm. Angular size is 7.6 by 4.7. Hey, why not? I don't think I've imaged this before. Jonathan, have we imaged M109? Jonathan is one of our, Jonathan, that person, is one of our students. He is the president of our astronomy student club, photo, Friends of the Observatory. All right. Whee! I really should be grading. I have a stack of labs that I need to grade. Oh, but this is way funner. And yes, funner is a word. Okay. Everything seems to be in place. Let's see if it's there. Oh, Jonathan, if you're still around, the camera is still tilted. Next time I do this, I might have people on Discord voice. Like do the whole Blue Marble Science where he has people on Discord. That conversation. Nice. One of the things that is on our purchase list is there it is. On our purchase list is a uh, zero point 0.5 focal reducer. So I'm hoping to be able to use those. I'm going to get a 2-inch and a 1 1/4 inch. That way we can hopefully be able to, because almost all of our telescopes are f8s. And so what I'm hoping to be able to do is use those to be able to see some open clusters at least, or extended nebulae at least visually. So yeah, there she blows. All right, let's go. Let's try to center this a little better. God, fucking donut, just meatballs. Meatballs. So again, Jonathan, if you're here, you kind of saw that it went up and went right and a little bit up. 1, 2, 3 licks of the Tootsie Roll Pop. So it's here. Maybe I should save this. Let me save this. M109. Start. I'm not crazy, right? That went right, well, right and up. Right? All right. Down is up. Up is down. People are watching. Thank you guys for keeping me company with this. I really appreciate it. What? Oh, I must be getting to clouds. That's probably what's going on. Although I don't know why that didn't go down. Oh, that's because it's 5 arc seconds. Good job, Rob. Good job. Up is down. I'm going to blame Jonathan for not catching that. Oh, I just read that. I think I'm going to. I think we should combine data. Okay, so I think it went that way. So I think up was up. This is weird. Our camera got tilted, so up and down, left and right is weird. So right. Okay. I'm going to fiddle with this. No, I'm keeping it there. Just going to keep it there. Right. All right, let's pop this up to 120. Bam! I really should adjust this focus. I think this focus sucks. Who knows? Not a lot of bright stars, so I don't think I can get a. Yeah, friggin' atmosphere. I think. I swear, sometimes life would be better if we didn't have an atmosphere. I mean, a container or something. Criminy. So it's what? 4:30 over there in nope 3:30. 3:30 over there in the UK. Yep, 3:30 in the UK. It is 11:30 here. Oh, I do not want to take flats. I do not want to take flats. I should cut that out. Oh, I lost somebody. 6:37 here. Thought you might be an early riser. Wow. Wow. That kind of sucks. I don't think we can do MO 109. So I'm getting almost no signal here. All right. We'll give it the good old college try. Tracking seems to be okay. Granted, I'm only doing minute-long exposures, but wait a minute. Wait a minute. Why am I not drinking? Why am I drinking water that's not caffeinated? Awesome. Now, do I have a mug? Ha ha! I think that mug is clean. Woo. Starting to get svelte. Yeah. Hope the sound's good. Mic is kind of off to the side. I need to move that. I don't know where I would put it. Well, that blocks my screen. Too far, I think, over there. Figure it out. Could move it here. Made you yawn. Made you yawn. I don't know how many of you know. I don't know how many of you care, but I'm tentatively going to be talking to Witsit on Friday night. So that should be fun. Yeah. IB, I don't think this is going to work. Could kind of see something. Oh. Yeah, I can feel some of you out there judging me. Yes, I am drinking instant coffee. But way easier than trying to bring a French press in here. Ugh. All right, buddy. I'm making an executive decision. Given clouds and given how tired I am, I'm going to put this on the back burner. I wouldn't mind trying this with like a 30-minute exposure. But la 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 la. I think M65 is too low. Air mass of 1.35. What is M5? I'm going to guess that's a globular cluster. It is. 23 arc minutes. I've never done M5, but I've imaged globulars on this channel before. I don't know if people want to see globulars. Oh, apparently he's onto rotational mechanics, which I didn't really know was a thing. Um, Basically, people who really, really want like Mach. Now, um, Nebula screen sky. Mm-hmm. Chain. Mm-hmm. No. Sombrero Galaxy. Ooh, where is Sombrero? Oh wow, that is really low. M 1.67 here, man. When's it set? 4 o'clock. So it's basically at the meridian. Oh yeah, I forgot. I'm north now. Last time I looked at Sombrero, I was roughly 8 degrees south latitude or 8 degrees southern latitude. Although that would make it worse, right? No, that would make it better. I'm not used to that being so low. Maybe not Sombrero. Rosette Nebula. 9. All right, let's try to find. 2237. That's not even up. Website, you were lying to me. Pinwheel in 101. Leo triplet. Sunflower Galaxy. Ooh, that looks pretty. 9.4. Bodes and Cigar Galaxy. Owl Nebula. Nope. The Whale Galaxy. No. Whirlpool. Been there, done that. Jellyfish Nebula to faint. Needle. Black Eye Galaxy. It's pretty faint. That's not what I wanted to look at. Here at magnitude is 9.3. Angular size is MOA. What the fuck is MOA? Minutes of arc. 8x2. What the hell? Let's try it. Black Eye is very unusual looking. It's the object I was just looking at. I think it's too small. Oh, yes, I want to move. Move, my pretty. Move. If I do this, that's better. Well, I should have been doing that the entire episode, the entire stream. But, Hey, is there somebody on my computer? I'm not in Rutledge. Go away. I'd like weather map, please. Radar. All right, anyway. I think I'm good. All right. Okay. All right. Expose. See if it's there. I was trying to bring up the satellite image to see if there are any clouds. Ooh, I think that's doable. Let's move it out of that area, though. If you were wondering, that linear line, that basically means that I think it's column. For some reason, I think this this view has been rotated. Basically means that in this case, row, although I suspect it's actually column, is dead. Is basically not artificially bright. It's a image. It's an artifact of the camera. So one of the reasons why we were thinking about replacing this thing is because it's getting old. Some of the pixels are failing. From a science perspective, it basically just adds error to your data. But you can't avoid it. Hey, all right. Let's go with that one. Let's see what it looks like at 120 seconds. Let's see what it looks like at 180 seconds. Let's just keep everything consistent. Holy shit. I took darks earlier and I took them at 120 seconds. This is why you take darks at the end. Oh, Christ. So those are useless. Let's see, what's new? Oh. So my meeting with my director is postponed till next week. We're going to talk about going to Uvalde for the annular solar eclipse. The issue is we have this big event called Space Day. which is later on that week. I definitely have to be here for that. So timing is going to be a little bit weird, or might be a little bit awkward. Also, I don't know if I don't know if I can get enough tour guides to blow off class for the eclipse is on Saturday, pretty sure. So they'd only be missing 4 days of class. I called the superintendent of Uvalde County or whatever region Uvalde is in, and they haven't gotten back to me. But I haven't pressed it because, again, I've been waiting to talk to Peter, see what he has to say on the thing. So, but I really, really want to do it. So, really, really want to do it. I just don't know how I'm going to make it possible. Worst comes to worst, I guess I could just throw a couple telescopes in the back of my car and with solar filters and just drive down there and find a school and be like, hey, check it out. But I'd like it to be more organized than that. But knowing my luck, it'll probably also be cloudy. So who knows? Wow. All right. I have never imaged this one before. That's impressive. Really nice dust line. Really saturated, although, oh, there we go. Kind of see some spiral structure. Let's see what this thing looks like in blue. So, yeah, so this would be a spiral galaxy. Obviously, you all can Google what M65 actually looks like in a good skull with someone who actually knows what they're doing in terms of astrophotography. I can see why it's called the Black Eye Nebula or Black Eye Galaxy. But it looks like a tilted spiral. Get it again. Oh, let's see. Yeah. Looks like a shit. Looks like a ring galaxy. Doesn't look like it has no kind of spiral arms off to the left and right. What do they say? It's an SAB. Yeah, sure. Ring. Yeah, yeah. It's the time of night when the Rob just starts muttering to himself. Wait a minute. Hey, Venus. This is taken with our planetary camera yesterday. The blurring is not the fact that it's out of focus. The blurring is because, it is really low on the horizon. Looking through a lot of atmosphere, you can see a lot bouncing around quite a bit. But that's pretty much what it looks like. First quarter Venus. Don't look pretty. Venus! Yep. See it bouncing around a lot again because of the bouncing around a lot. It's cold -3, by the way, because one of my students just decided. The first one was video. So the second one, he was trying to rename it Video 2, and it came out -2, and he was like, all right, fine. And then, of course, the next video we took had to be -3. So there you go. Oh, it's done. This is blue. Well, shoot. You can almost see the ring. So some galaxies, they have a ring structure. So instead of spiral arms, they actually have basically a ring of dust and star formation around a central region or the bulge. This one seems to have that. You can kind of see that in blue. All right, I'm sold. I probably should touch up the focus, but so it took about 2 hours. I am not sitting here for 2 hours because I still have to do calibration frames. So signal noise sucks. I'll grant you that. I'm going to do it anyway. First time, ladies and gentlemen, and others. Let me make sure. M65, apply, okay. Start. First time imaging M65, for me anyway. Let's bring this back up. Ta-da! Bilbo Baggins's galaxy is a ring. My precious. I guess that's Gollum Burns. My precious. Nice. Warm in here. Looks clear. This is all the data we have taken here at George W. Mason. We have been taking scientific data since 2013, mostly on exoplanets. Let's go down. No. Let's see if we can play around with this. Search. I think this negatives it. Ooh, negative image. So cool. Medium. This indicates that what I'm doing here is you have what is called screen stretch. Oh, it's downloading. Okay. Screen stretch. So I mentioned before, ripping through this coffee. I mentioned before that that the pixels have 65,000 some odd counts to them, but the computer can only display that over 255 channels. So you basically have to figure out which counts correspond to white and which counts correspond to black, and then you can stretch it. So basically, think of it as contrast, kind of, sort of. So, and brightness. Yeah. That's a little cold. All right, what else can we do? That's kind of shit. That's worse. Hmm. Hmm. Mm-hmm. Yeah. That's a. Oops. Where'd my screenshot go? Let's see. What else can I do with this? Mm-hmm. Let's see what flat background does. Oh, I guess select background. Boink. Doink. 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 Yeah. Much. Yeah. Let's try that. Gaussian blur. That doesn't seem to do much. This is me just messing around. Hey, wavelet filters. I have no experience with wavelets. So I'm just going to click. Ooh, that's pretty easy. Way better, easier than deconvolution. You can definitely tell that these things are donuts. Ah! Normal. Better. It's not as donut, or it's not as shadowy. Let's see what the Mexican hat does. Nothing out of the ordinary. I would be explaining what I'm doing, but honestly, I don't really understand what I'm doing. All I know is what I'm doing is I'm applying certain filters to the image to try to increase the resolution. Essentially, I have no experience with wavelets. I've heard they're great, but I have no experience with them whatsoever. This is one of the reasons why I'm not very good at astrophotography, because I just don't put the work in. I freely admit that. I freely admit that. If I put the work in, I would probably know better. I'd probably be better at this. But that does look better. I might have to revisit this later on when I'm putting these things together. I forgot. I haven't been keeping up with Stanley Cup. My the lightning are out, so because of a friend, I've got to I've got to root for the Leafs for some reason. Why am I rooting for Canada? I kind of look at it as I'm rooting against the Florida Panthers. Fuck the Florida Panthers. But the Leafs, being the Leafs, are on the verge of elimination, but they finally won a game, and to prevent them from getting swept. So, haha, I guess. All right. Are we in the semifinals? No, we can't be. So we got. I guess I could root for Vegas after the Leafs disappoint me. You too. Wavelets really make a difference on planet. Yeah, that's what I've heard. That's what I've heard. I've heard that wavelet deconstruction or what have you, really good at bringing out the details of planetary work. But like I said, I know pretty much nothing about them. Good night, Chris. Thank you for hanging out with me. Yeah, hope you sleep well. I'm pretty sure I will once I get to sleep. Once this is done. Ooh, IB, I just saw the GIF that you posted um, on Tartaria. I'm assuming that is Io Shadow. Very nice, very nice. Um, no problem, IB. Thank you again. Thank you for being here. I know at this point it's probably not all that enthralling, but hey, um, it's been 3 hours and 18 minutes. That was IO. Yeah, I figured it might be. Very cool stuff. Very cool stuff. Oh, it was Jim Waterworld who tagged me on this. Uh, I'll respond to him. Why not? That's not what I'm going to do. Ah, another image of. It's another bit of IO's work, or another bit of IB's work. Oh, so this is probably before the shadow. Yeah, this kind of. Oh, that's Europa. That is good stuff. That is. Yeah, that is amazing. Might need to get a DSLR for our observatory. Um, I was hoping that we would have one of the students would have one that we could just strap onto the 32 inch to see what we can do with it, but can't really justify the cost of having a DSLR just to basically make pretty pictures. Um, but it would be nice. Maybe I could borrow one. Oh, wait a minute. Novak might have one. The Northern Virginia Astronomy Club, which I am a member of, they have a loaner program. Maybe I can borrow a DSLR. That is a great idea, Rob. I'm so glad I found it. I'm so glad I remember that. Yes. Oh, uh, I don't know about the model, but ZWO. Yes, that is definitely going on the wish list. Thank you for the reminder. Um, I need to. So I'm compiling a purchase list. So when after June, when the fiscal year goes, when our basically we get our budget back, when the fiscal year goes to 2024 or whatever, I'm compiling a list of things that we need to purchase. 3 Telrads, some focal reducers, and yeah, I'm going to see if I can convince Peter to shell out the money for a ZWO planetary cam. See if we can replace that old fucking webcam that we're using. So, yeah. Some of the images I showed you, the planetary images I showed you before, Owen, our student Owen, took with his own ZWO. But I don't remember what the model number for his was. Ooh. We have that from EMBO, who I gave the link to for this stream. I don't know if they are around, but that is pretty damn awesome. That can only be Venus. I'm thinking that can only be Venus. So basically a lunar occultation of Venus. That's damn pretty. That is. I'm going to have to give that a thumbs up. Although I can't seem to. I'll just reply. Da, da, da. Jim the Water World. What am I going to do with them? Okay, now that's just funny. We on? That's visual. What air mass are we at? 1.12. Focus sucks. The other problem with that I have with astrophotography, and this is something I know, but I still don't do anything about it, is that I'm impatient. Um, I just want to start taking images, and so I don't. And I don't want to fiddle. I'm not a fiddler, so I know the focus is. I know the focus can probably be improved, but I don't want to stop and play with it because I feel like I'm going to miss out on taking data. So I don't know. I know this about myself, and yet I still don't do anything about it. Do, 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 do. Who's spamming that? Oh, apparently Andy Hold My Beer is really into numerology. Really into numerology. La 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 la. Let's see what's going on Blue server. Eric E just spamming atmospheric stuff. Okay. I really, really hope I can tease this out. Play around with those wavelets. See if I can get that to look any better. Oh, I can. That's cool. Well, now I'm excited. I'm getting a little bit excited. Play around with this. When I do the stream, probably this weekend, you guys will get a front row seat on just how bad I am at astrophotography. It's going to be awesome. I'm excited for it. I don't know about y'all, but I am excited. Maybe I'll get some folks on that actually knows what they're doing with image processing, and they can tell me what I'm doing wrong. Ooh, all right. Now we're talking. I just changed the stretch. I didn't even think about trying to change the stretch. That's pretty. Ooh, I'm getting excited. Now, if I can just tease out the background, this disc. So I think this is the ring structure around the galaxy, which means this is really blown out, which is weird because it's nowhere near saturated. So I have to think that this is a angular resolution problem. It's got to be an angular resolution problem. See what happens if I do this. Okay. That's a little too extreme. Still too extreme. What if I do cubic spline? No, worse. Of course, I can crop that out so people can't see that star. And of course, this hasn't been calibrated. So this, whatever this is, which is probably a dust way far away, maybe on the secondary, um, that hopefully will go away. IV just posted an image of. Well, I just do this. There's IVs. Very nice. Very nice. Nice color balance. I like it. See, this is another thing that I want to figure out how to do is, or a problem I have is, I want to get the background black. I don't like the fact that my backgrounds are pixelated like this, where you can, it's not just flat black. Might have to cheese out and try to do that in GIMP. Oops. More Venus. We're going to shut this off. Check my email. Nothing important. Check my work email. Got a meeting with my department chair tomorrow to discuss my Future here at George Mason. How I can get on multi-year contracts. Hopefully, I'll be able to. Let's see how it goes. It's all right. Yeah, nothing else of really any pressing emergencies. So, don't forget to like, share, and subscribe. All 2 people, 3 people watching. Sorry. Thought I was going to do a stream about using on data analysis for Cephians, and then I realized, yeah, that might be a little too advanced, as it were, for someone who has never seen this sort of thing before. Like, oh yeah, you really do need to know a lot of basic concepts in order for this to really make sense. So I probably won't do that. Or if I do, it'll be more of a demonstration kind of thing rather than a tutorial kind of thing. And I don't think I'll do it live. I know that I won't do it live. I'll actually do an edited video for once. Thank you, Judy. You are amazing for so many different reasons. Thank you for being here tonight. And thank you for the donation. Ooh, I've been tagged. Don't know what that's supposed to mean. Sorry, I'm looking at Discord, so I will probably get trapped in this. It's red. Hey, I'm on my red images. Sweet. So fairly soon I will. There's definitely a lot of extended dust emission. I actually have some hope for this, and I think I'm going to return to this. I'll sick the put my students on this photo and get them to put this into their their observing schedule. Now, yeah. So here's a classic example of a ring galaxy. This more than likely, well, I probably shouldn't say classic example. This, I suspect, it's not lensing. Um, I suspect what's happening is that this is after some kind of collision with another galaxy, probably with that galaxy right there. Oh, it's very clean. I don't know. I'll have to look that up. Very, very pretty image, though. I don't know if I don't know if Embo took that or not, but oh. Hey, Embo, I was just showing off your galaxy image. Howdy, howdy. I am currently, as you might know, currently imaging the Black Eye Galaxy. This is a 180-second exposure in red. I've already done and blue and green. And then after this is done, I've got, I think, two more of these. Well, three more of these. After I'm done there, I'm going to start taking flats and, shutting things down. But thanks for popping by. I am actually going to use the restroom because I've been at this for basically 4 hours. So, yeah. Hopefully the telescope doesn't explode while I'm going to the restroom. I'm back. This part of the stream brought to you by George Mason University College of Science. La, 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 la. What is that object? Embo, if you're here, if you're here, what is that? What's the name of that object? I'll try to image it. As while we're at it, what is the name of that object? I'll try to image. Fairly certain those are going to be too faint, too small, but I'll give it a good old college try. Oh yeah, yeah. I mean, I'm familiar with the light rippling effect, but it's been a while since I've looked into it. I know it's fascinating to watch me get on my, my thing, type on my computer, type on my phone. Einstein's cross. That's what that is. Einstein's cross. That's what. For those of you who are still watching or watching at home, watching later, that's Einstein's cross. I knew that object. Lens quasar, yeah. No, not. All right. Oh, I am done. I am done. Dun, dun, dun. Now for the really, really boring part, which I might shut down the stream for, but not that anyone is actually watching. Well, I think maybe one person is. Maybe three people are, theoretically. All right. So what I'm going to do now is I'm going to take calibration frames. I thought I had taken care of that in some of them in the beginning, but no. Apparently, I messed up the darks. But I am now going to take flats and show you all how that's done. So let's do this. Dome flats, assuming that I have not been lied to, and the dome, the flat field controller actually works. Okay. Hey, we have a flat lamp. Awesome. Awesome, awesome. All right. So, let's see here. Thank you, Emma. Yeah, I'm actually rather excited because I'm actually pretty friggin', I don't know why, but I am pretty friggin' exhausted. I'm going to close this up, and then I'm going to park it. And I'm going to reposition the telescope to take flats. While I'm doing that, no, wrong. Jeez, I'm exhausted. Getting old. I can't do the all nighters anymore. Autosave. D2. Oh, yeah. Man, I gotta clean this stuff up. All right. Okay. Lower shutter just closed. Top shutter is, hopefully you can see from here, is closing up. So if you were wondering how the shutter works, that's how it works. We got a lower panel that flips up, and then the upper shutter rolls down. A computer pause it actually. All right. Okay. Now that the dome is closed, I'm going to park it. Oh, yeah. For those of you curious, that, I don't know if that's IVs, I'm assuming it is. That is what I'm imaging, the Black Eye Nebula, or Black Eye Galaxy. Hopefully I can get as cool an image as that. Okay. All right. What am I doing here? La 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 la. Messages. General. In. Okay. Oh, this is all right. Yeah. All right. So now, what you want to do is you want to make this as quick as possible. I mean, I could take flats here, but it's not very bright there. The idea of a flat is you want to take an image of a perfectly illuminated field, of an evenly illuminated field. Now, as you can see from the dome, that is not evenly illuminated, not really even close. But if it's going to be so out of focus that it can approximate that. But I will say that our flat fields aren't great. I've been trying to figure out a way to fix that, but for what we do, it works, I guess. So I'm going to come over here, and that is not what I wanted to do. I know there's a way to input coordinates. Probably want to go over here. Tools, Sluter coordinates. Woo! All right, so long time ago, 2 years ago, in fact, almost to the day, I figured out the best place to put the telescope, but this is probably not going to work because flat lamp has probably changed positions by now, or since. So, altitude of oh, I flipped those. Oops. What's the ideal size for imaging like this? Are you talking telescope aperture? This looks strange, even for. Well, that is not 80, that is not 45 degrees. Um, Ideal size for imaging like this. For this kind of object, I'm going to assume aperture size. You're going to need a fairly large telescope. I don't know if there's an ideal size, but I wouldn't really try to do this with. I would say you'd need at least a 12-inch, maybe 16. This is a pretty faint object, and I was doing a few minutes of exposure. If you go down to 12 or 16, you can do much longer exposures, but your mount has to be very, very good because if you have any kind of tracking problems, you won't be able to get the long exposure times you need without a significant amount of trailing in the image. And yeah, what the? All right, so I told it to go to 57 degrees as and 45 degrees out, and it went to 360. Oh no, it didn't. What what is going on? No, that says what it is. All right, I'm just gonna have to do it by hand. Fuck it, I'll do it live. All right. Okay. No, I can do it this way. Let's do it this way. Never done it this way before. Oh. Nope. Mm-hmm. Slewing the target. Slewing the target. I just realized I could probably do this a different way. This does give you a nice view of the inside of our telescope. That is our secondary mirror. I'm not going to lower this enough to actually give you a view of the primary because I don't really like doing that. Not that the mirror is going to fall out, but it could cause the mirror to. I'm paranoid that it's going to cause the mirror to reposition, which is going to affect your collimation. So I don't like doing that. Although my director seems to really like doing that. What am I doing? I'm just falling asleep at the wheel. It's not what I wanted to do. All right. All right, I think that's good enough for government work. So, what do I want to do here? I want to take a single exposure in B. Let's go with 30 seconds. Oh. Peyton, I hope that answered your question. An embo, yep, that is the same one I'm imaging. Let's see. Hey, Professor Parks, just say stationary topographical plane 3 times. You might make it. Stationary topographical plane, stationary topical plane. So I screwed that up. Stationary topographical plane, stationary topographical plane, stationary topographical plane. Nope, no Beetlejuice. You came in at the very end of this science. I can real quick, since you're here, I can show you what I've imaged tonight. Just kind of wet your whistle. So that is an unprocessed image, obviously, of the Whirlpool galaxy in the V filter or green filter. And so I took a whole bunch of those. And then later I went to the black-eyed galaxy and then took this. Actually, I'm going to show you a red image. Those are much better. Those look cooler to me. Cooler, red. Get it? All right, never mind. I'll stick to my day job. Doink. I've never imaged this before, so I'm actually pretty excited about what I can do with this, or likely what my students can do with this. So here it is, black eye. What's that little line towards the bottom middle of the images? So I suspect I know what you're talking about. Oh, this. Funny story, that is a piece of cotton. Because we had some kind of weirdness going on with our CCD camera. Basically, we were getting this weird, just global artifact on it, and so we decided to clean the piece of glass that is in front of the shutter. And my director decided to use cotton balls to do it. And yeah, so that's a little remnant from that. And yes, aliens. I would like to think so, but no, it is in fact not aliens. All right, so with flat fields, you want to get. You can see here. I don't know what that is. That is some kind of smudge. I almost want to say it's a fingerprint. Some kind of smudge in the optical system that's being imaged out of focus. These are dust particles that are probably, because they're so small, they're very close to the detector. So they're probably on that piece of glass that I was talking about. What I'm a little, oh, there it is. I was zoomed in. I was like, there it is. There's the little doohickey, a piece of cotton. So a flat field, one of the jobs of a flat field is to get rid of those, that little basically artifact that you were Peyton, you were talking about on those images. If I flat field correctly, then I should get rid of those. And like I said, this is supposed to be evenly illuminated, and you can see that it really isn't. So it really isn't. Okay, I need to see if I can reposition that. I need to do something about that. All right. Let's go. Maybe it's too far down. All right. Let's try this again. This is in blue, so the Actually, now that I think about it, I may have just made it worse. This is in blue, so it is the least sensitive. Well, of the three, blue, green, red, it is the least sensitive of the three. So the telescope just it takes a longer time to get the same signal in the blue part of the spectrum than it does in VRR. Um, so, besides, you just got home. Oh yeah. So it's what 10 o'clock. All right. Oh, hello. I think that actually improved it. Yeah, it did. All right. Uh, oh, I'm a moron. All right. Those coordinates were correct. Oh yeah, graduation is, I think it's this week for us too. Um, now I remember. Yeah. So I pointed at the very beginning of this. When I told this to go somewhere, I was pointing on the opposite end of the dome, which I thought was wrong. But in fact, I want to do that in order to avoid this, to make it evenly illuminated. We're too close to the lamp, and so that is what's causing that differential. So yeah, all right, it's early ish. So let's go over here. Were you actually a part of graduation? Like you got you wore your PhD robes or your robes or what have you? Uh, and because I've never done that. Like, what were you doing at graduation? I've never worked graduation. So the other thing that I want, other than an evenly illuminated surface, is these counts here. So you can see this is about 4,500. This is about 5,500. I want those to be closer to 30 to 45, somewhere in that range. Um, Student showcase stuff. Yeah, all right, cool. So you can see with 30 seconds, this is going to probably. Do I have to go 90 seconds? Jesus, you need a better lamp. Um, Showing all this stuff, nice. Is this in your department or is this university wide? The people showing their stuff. Other departments. Okay. Let's say cross departments. CS kids and other kids from other schools. All right, cool. Other departments, I should say. Nice. Very cool. Um, sorry, I'm a little bit distracted with Discord. I really should be paying attention. Sorry. 6,000. Holy crow. At 90 seconds. Need a better light. But, oops. I think I need a brighter light. Good Lord. I think this is pretty evenly illuminated. So, yeah, it's still got a problem down here. But I think it's as good as it's going to get at this place. I really need to figure out another way to do flat fields. Why'd you say you were imaging this with the blue filter again? So if I bring up one of these images again, let's do that one. As you noticed, you have the squiggly doodad down here. I want to get rid of that. So that is an artifact of the camera. That is the fact that there is a piece of cotton on the CCD chip shutter window thingy. So I want to get rid of that. And the way that I do that is by taking an image, what we call a flat field, flat because theoretically it's supposed to be evenly illuminated across the surface. That will count for two things. That will get rid of all of these little dust motes and things of that nature that are again artifacts because of just pieces of material in the optical train. But also it will take care of any sensitivity differences between one pixel to the next. So I need to do this in every filter that I took images in, B, V, and R. And oh my God, it's going to take forever. I think I'm going to have to do 180 seconds on B. Normally flat fields should be seconds or fractions of a second. This is ridiculous. I need to figure out a way to. I don't know. We need a better lamp. This is ridiculous. Flat field should not take 180 seconds. Oh my God. We'll be here until dawn taking calibration frames. So, just to reiterate, if anyone is going to watch this later on, what I'm doing here is I am, again, pointing at the dome in order to get the illumination as flat as I possibly can. And I want to get enough signal, basically around 20,000 counts at the very least. I want to get around 20,000 counts so that all of the pixels are very well mapped. Basically, all of the artifacts have a lot of signal to noise. The variations in brightness from one side to the other, that has a lot of signal to noise. So that when we do the flat fielding, we characterize those artifacts and those sensitivity differences very well. Taking a blank image, capturing what is just part of the camera, and that then subtracted from the sky. Actually, that is true for subtraction is true for the bias frame and the dark frame. With flat fields, you actually divide the image. You're essentially normalizing the image. Because if you did a straight subtraction, and you may have been using subtracted as a just as an ad hoc term, but if you do just a straight numerical subtraction, then because the counts are so much higher than the science counts, you're basically going to get a weird inverted image. I I have Discord over here looking at the Tartaria Discord. I have a weird relationship with Jim Waterworld. I don't know how the hell that happened. Yes, yeah, I figured as much. Yeah, subtraction in the colloquial sense, um, where you basically get rid of it. So, but technically speaking, it is a division. It is a division. All right, 180 is as far as I go. I am not taking a longer exposure because that is redonkulous. Please be of sufficient signal to noise. I'm going to guess it's around 15,000. 12. Oh, that bugs me. Oh. Oh, that kind of tells me that CCD camera is not linear. Oh, Christ. Too tired to deal with that. All right. 180 or bust. I'm going to have to, that is going to have to be good enough. Wow, that is just that is a huge spread. So the brightest parts are around 1400. The dimmer part, you got a 12 or 2,000 count difference between the bright and the. Guessing that's vignetting? We might actually have a vignetting problem. How have I not really noticed this? Okay, I'm too tired for that. Anyway, let's just get this done. All right. So I'm going to be doing that. And hold on. V. Let's go to 60. Oh, Lord. So what I meant by linear is CCDs should be linear. And what I mean by that is if you take a 10-second exposure and in a particular pixel you get roughly 10,000 counts, if you double that, if you go to 20 seconds, then the exposure should be 20 times. Or excuse me, 20,000 counts. It should, if you double the exposure time, you get double the counts. Triple the exposure time, triple the counts. This is pretty vital if you want to compare differential photometry from one night to the next. From one night to the next, you need the chip to be linear, which it's looking like it's not. 30,000 counts! Yay! It's 60 seconds. Good Lord. I'm going to be here until dawn. All right, so 180, 60. I think I can get away with 45 here. Oil floats on water. Is that gravity or is it density? Both? I'm going to go with both. So science, I am, theoretically, I am going on Witsits on Friday. I have a plan. Hopefully it's not the biggest mistake I've made in a while. Good Lord. Oh, wow. 60. This is nearly saturated. So the top of the so the max, the number of counts that we can possibly get, total counts that we can possibly get, are 65,635. If you expose longer than that, you're just wasting photons. You just it doesn't matter. We definitely don't want to saturate for the flat field because, again, if we saturate, then it's not an accurate representation of what this looks like. But so I need to lower this considerably. If it's half, I'll go for 25. So I'm not quite half, but yeah, close enough. So what this tells me, and I'll answer your question in a second, Science. What this tells me is when I'm looking at this is B is 180, V is at 60, R is at 25. So yeah, there are different sensitivities between the blue filter, the green filter, and the red filter, but red and green really, unless I'm missing something, should have the same throughput, should have the same sensitivity. So what this is telling me is that the light that we're using is redder, is not white. It's actually closer to red than anything. Sweet. So if you all were paying attention, hopefully I did this right. So this way. Let me call this flat. 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 V. R. I think I said 60. Hopefully I'm right. This is 25. I'm only going to do 5 of these because, yeah, I want to be here forever. If I'm doing 180 of, might as well do the darks too. What the hell? Call that calibration. Flat we. Flat. Oh, oh. Oh, oh. Flat R. E. Apply. Let's do 6. 6. Now I'm just being silly. Okay. Let's start that. Woo! Oh, I need to turn tracking off. Okay. So the plan is, I really want him to. I really want to learn from him. I'm not going to get into specifics. I want to be a surprise, but I want. I want him to tell me with specificity. Why is it? Who's pulling my strings? If if the Earth is flat, and all that, then as a professional astronomer, obviously I disagree with that. Obviously, from my training and my experience, the world is not flat. The world is a globe. Relativity, GR, pretty much works. It has some flaws, or it has some things that can't quite get right yet, but it works. So why is it that of this opinion, and don't realize after, all of my education, all of my work experience, why is it that I don't know that the Earth is flat and the universe is electric, blah blah blah. Gravity is electrostatics. Um, Obviously, somebody must be controlling the narrative. So I would like him to tell me who that someone is. Or at the very least, if someone is not controlling the narrative, then why it is that the overall scientific community, thinks that their world is a globe and GR is a thing and all that kind of good stuff. La 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 la. Yeah. Wow, I'm tired. That sort of thing. GR is 96%. Okay. I'm going to ask, are you kidding with that? Because from what I have been told, GR actually predicts the orbit of Mercury exceedingly well. But I've also been told by Alan that it's actually it's been backwards compatible, essentially, or backwards engineered. So I haven't really looked into it, but from what I have been told, that it actually predicts his orbit very well. Oh, okay, got it. I will look up on that because I've been meaning to respond to Alan's 3-hour lecture on relativity. And what the fudge is that? I've seen this before. I actually highlighted this in one of the images that the students took. I've seen this before in a different telescope, and I can never figure out what it is. What I'm talking about are these arcs. It's got to be electric noise, but because they're really there, it's not a display issue. But I have no idea. I don't know how significant it is. It's just bizarre. It's got to be. The only thing I figure is that it's coming from the filter wheel, and it's somehow some kind of electronic interference. Yeah, I'll look into the. As I was saying, I'm going to respond to what's it called, Alan's 3-hour lecture on relativity. That's something I'm going to do once the semester is done. Oh, where he makes claims like the Eddington experiment is wrong. Mercury's orbit is back engineered. And since I haven't watched this 3-hour lecture yet in its entirety, he makes some other claims. But so I want to look into that. Not because I really want to debunk it, but because I don't really know the specifics. And, I teach cosmology, an introductory sort of qualitative cosmology class in the fall. And I think it would be beneficial for me to have this information because it's just more learning, and I can teach it to my students. So it's not a bad thing for me to know more specifics on the fundamental underpinnings of relativity and how it's proved. So, since this is a dark frame, the shutter isn't open. Oh, wait a minute. I think it's afterglow. I think it might be some afterglow. Is what we call it. Basically, when the pixels haven't flushed out all of the light. I don't know. Maybe. Although, why wouldn't that be in the flats? Let's see if it's actually. I think you might be onto something, because obviously they're not there anymore, or not as there anymore, which would indicate that this is some kind of ghost image, that it's not flushing out the camera. Matt, this is why I like having you around, because you're smart and you help me figure stuff out. I think the only question I'd ask is, are you trying to use advanced science to debunk basic science? Yeah. I mean, that's also one of the things that I want to get at is, he's rejecting GR for reasons, and he's going to, I won't call it fringe, but ideas that have been put forth by academics as an alternative explanation for gravity, or GR rather, but just haven't been fully tested. So he's putting his faith basically in something that is still in the sort of formation theoretical well, not theoretical, but still in the formative stage and hasn't really been tested by the community, and just rejecting something that has been very well tested or rigorously tested. So I don't quite get why I think I get it, but I don't want to assume. Yeah. Apparently, he does. Apparently, one of the things that he's doing now is, and I didn't even know this was a thing. Again, I now know it's a thing. I've heard of Mach. Ernst Mach, I think is his name. In the sense that of the principle that if you have a singular object in the universe, if the universe was only comprised of the Earth, for example, it is impossible to state that it is rotating or moving in any way, because you have no frame of reference upon which to compare it. That is as far as I know of anything dealing with Mach's principle. But apparently he's got this whole, what was it called? Did I just say it? I probably just said it. Rotational something or other. Let me see. Eric E. has been sending me this. Apparently an entire field of study, relational mechanics, which I've never heard of. Which basically states that, I don't really know what it specifically states, other than the fact that it says that GR is not a accurate representation. This analysis clearly shows that in general relativity, kinematically equivalent situations are not dynamically equivalent. Yeah. That's basically the impression that I'm getting, is that that Mach's ideas, or apparently this whole field of relational mechanics, not a lot of people accept. Apparently, there is one specific physicist who is fairly well known for accepting it or putting it forth, but yeah, he's apparently not very well considered for. He's not very. People don't really respect it, I guess is what I'm trying to say with that. All right, folks. So yeah, I actually if this is counters correct, I have 6 people watching. I am in the winding down phases of the night. I'm taking calibration frames, which I will use to calibrate the images I took over the last 4.5 hours. And and then I will be putting the telescope to bed. Um, I was thinking of just signing off at this point because I didn't think this would be overly exciting. But since Matt's here, I can just chat. So I'll just keep it up, and I'll break my record. I think I'll break my record for the longest stream. My other record is my conversation with Sleeping Warrior. I think that went to 5 hours. Right now we're at 4 hours 42 minutes. Oh, Lord. So see how it goes. And yeah, that I think you're right. I think that's just I think that circular business. I don't know where it's from. I don't know why they do that. Why it has that form. But I think you're right. I think that's afterglow from that really bright, like near saturated image that I took earlier. Ooh. Somebody put the Lorentz factor into Atari. Do 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 do. Jim apparently wants me to find 12 PhDs to debate him on the globe. And my response is, why 12? Okay. All right. I might do that. I know one of the things I've been told one of the things that he seems to be going seems to be a favorite subject of his recently is uh, uh, apparently the Foucault pendulum, as he states it, the Foucault pendulum can no longer be used uh, to determine the rotation of the Earth because apparently from this textbook that he's been skimming, uh, there's a quote from that, or it's a line in there that essentially says that same thing. Peyton, yeah, that is kind of an insane request. Um, I don't know why he thinks that why he thinks that I could do, or why he thinks that 12 uh, PhDs would debate him. I can. Are you talking about Jim or what's it? Probably Jim. If you're talking about Jim, I actually don't think he's being disingenuous. If he wants 12, well, it's got me, although I don't really like debating. Um, he's got Phil, Tony, Clive, so there's four. But why Why can't you do this, Jim? Oh, there you go. Oh, great. Somebody is trying to I think someone is trying to diagnose Jim with autism. Yeah. I don't know if I would describe that as disingenuous, but I agree with you on that. And it's interesting to me that, with other flat earthers that I've encountered, they don't believe in basic science. They think basic science is wrong, and they just leave it at that. They just, they that's it, and they'll default to, well, I can't, you show me proof, give me a demonstration, or give me an experiment, really a demonstration of it, of gravity working. With Whitsitt, he's one of the few who actually tries to use science, in this case, complex, fringy science, to debunk basic science, which is new on me, and I'm really curious to know what his why he. I'm really curious to know his response to the question of, why are you doing that? Why is it that you have, like I said before, do not have faith in GR, but have faith in the electric universe, relational mechanics? Can't remember the other one, the electrostatics. Yeah, I read a paper by Mies, which talked about electrostatics as a explanation for dark matter. I don't know. A lot of math. I honestly didn't quite understand where the math was going. Oh, and you're not missing out much with Jim. He doesn't really have a lot of arguments. Jim basically just insults people, except me for some reason. I don't know. I got on his good side. Okay. Image 6 out of 20, or image 7 of 24. Oh. Then I could put her to bed and go to sleep. Well, a while ago, maybe a month ago at this point, I was on Discord with him, and he seemed very, very keen on basically doing what's his face, what Tribune wants to do, which is using. He doesn't want to use. Whitsitt doesn't want to use mirror flashes, but he wants to use lasers, and he wants to do a laser test to show that the Earth is flat. And I was like, what you need to do in that case is you need to get with folks who understand refraction and help you design that. The exposures are shorter on the later ones. Yes, you're correct. So these are the darks are 180s, the blues are 180s, then the V's are faster, than the R's are fastest. So yeah, you'll see a lot of darks. You'll see a lot of darks. You'll see a lot of blue flats, and then hopefully it'll go quickly for whatever. So, actually, I think it's over the salt flats. He does not want to do it over water. He wants to do it over some kind of salt flats, either in Utah or somewhere else. At least that was what he put forth. So. Peyton, are you a student here at GMU? I want to say that you are. I probably just embarrassed the shit out of myself because you might have been one of my students. Um, which, in that case, I really apologize for my Astro 103 class. Let me just rephrase. Peyton, have you taken any of my classes? Oh, you're in photo. Okay. Because, yeah, if you had taken 103 with me, which I'm going to talk to Paul tomorrow, and I'm hoping that I can get 103 back. You've taken 103 with me, it's hundreds of students, so I don't remember anyone else. Hope to one day I'm studying astrophysics right now. Sweet. Can I ask what year you're in? My hope, sophomore semester. Okay. Um, so yeah, I'm discussing with my department chair. I'm having a meeting with my department chair tomorrow. Hopefully, I will be awake for it. And we're gonna essentially have a powwow over my future at George Mason. Essentially, I think what we're going to talk about is um, how I will move to multi-year contracts and what courses I'm going to be teaching. So I'm hoping that he will put me back on 103, and then keep me and allow me to keep with 302, which is the cosmology course, the qualitative cosmology course. And I'm hoping he will actually allow me to start teaching recitations, physics recitations. I've been teaching them this semester for the first time, and I miss it. I like. I used to teach physics labs, and I liked the straightforwardness of it, in that you have you can derive you have a certain you can derive equations, and then you can basically hold certain variables constant. Basically, you can test stuff, and at the end of the day, you have a yes, this is right, or no, this is wrong. So it's to me, it's much more tangible. I don't know if I'm describing this very well, but it's a much more tangible kind of thing um, uh, than just teaching qualitative astronomy. I hadn't thought about doing that, but I might. Um, I might. What I wanted to do, I was meant to have a meeting with Peter, who is the director of the observatory, today, but one of his twins was sick, so we've pushed it to next week. Um, and I didn't really, and so I called the superintendent of Uvalde County, or wherever it is, the Uvalde school system. I contacted their office and hoping to get an appointment to talk to the superintendent, because I don't know, the school may in fact be demolished. So I couldn't get any information on any instructors. And so I figured, I'll just go to the top person and see what happens. But unfortunately, they haven't gotten back to me about scheduling an appointment, and I haven't really reached out to them again because I wanted to talk to Peter first. Yeah, so yeah, I could swing that with Paul. So I could swing that with Paul and see what he has to say about funding. Yeah, it's something that hey, we're on B flats. Woo, we're halfway there. And what am I talking about? Something that just occurred to me today, or tonight is I believe the eclipse is on Saturday, but that would essentially mean that any tour guides that come with me are going to basically have to blow off at least 3, maybe 4 days of class. So, because we drive down there, and more than likely drive down there. Yes, we would have to drive down there because we would take the planetarium. We'd drive down there, which for me, I could do it in a day because it's 14 hours. But I'm fairly certain the students are going to stop. So, for those of you who might be watching that haven't been talking about that, what I'm talking about is in October, I think it's the 14th, it might be the 18th, sometime mid-October, there is an annular solar eclipse, which is going to pass through North America. It's going to come in somewhere around Oregon, I think, and it's going to arc through the continent of the United States into Texas and then leave out the Gulf of Mexico. And Uvalde, the Robb Elementary School in Uvalde is pretty much dead center. It's very, very close to the total, like the dead center of totality. They're definitely going to see an annular solar eclipse. They're not going to see a partial eclipse. They're going to see a total annular eclipse at that location. What's even cooler is in April of next year, again, I don't know the specific day. I think it's the 24th. Could be very wrong. Might be the 8th. Who knows? You can Google it. There is a total solar eclipse that's going to pass through North America, kind of go in the opposite direction. It's going to come in through the state of Durango in Mexico, and then arc through Texas, and then go out through New Brunswick. So those two paths of totality cross. And as it happens, they cross right basically at Uvalde. So Uvalde is going to not only see an annular solar eclipse, but they're also going to see a total solar eclipse. So the original idea was not so altruistic. The original idea is I want to go down to Texas and view both eclipses if I can, if weather will cooperate, view both eclipses from the same location. Because I've never seen a solar eclipse other than partial. And so I just kind of want to have that that controlled, I guess, experience of being able to see two eclipses from exactly the same location or thereabouts, and just to kind of see what the experience is like. And then I was like, wait a minute, I'm going to Texas. How can I make this bigger? And, can I make this into an outreach event? And I was like, wait a minute. Oh, where is Uvalde, Texas? And I looked it up, and yeah, sure as shit, it's really next to, it's near San Antonio, so it's really, like I said, it's optimally located. And so I was like, you know what? This needs to happen. I need to, instead of just bringing down telescopes, I need to bring down my inflatable planetarium. Because I was also, along these lines, it's kind of two separate thoughts that combine. Have this inflatable planetarium, have planetarium will travel. Recently, we've been taking the planetarium to more and more locations. And I was like, where can I take it? And where can I take it that would be most impactful? Like, I don't want to take it to where, where the rich kids are, the kids that have can easily go to a planetarium or what have you. Or in this town, there are a ridiculous number of high schools that have permanent planetariums in them, which is just, oh my God. Anyway, so I'm like, where can I take this where, folks that really would never be able to see this would get advantage of it? And then the Uvalde thing came into play. I was like, yeah, I want to take my, because even if the eclipse doesn't happen, or excuse me, of course it's going to happen. Even if it's cloudy, what I can do is I can do planetarium shows to illustrate what what it would look like. Yeah. I'm not. If you went to school in this area, I'm honestly not surprised. There are just a ridiculous number of high schools with planetariums. I'm like, before I came here, I've lived in a lot of different places, and if you could find a planetarium in that area, that was a good thing. Like, I mean, that was kind of a rare thing. Not here, not here. Find them at any high school, whatever. So with the Evaldi thing, also, you get the you can do the whole poetic thing where obviously with an eclipse you have a bright sun that's eclipsed, it's darkened for experience a period. It experiences a period of darkness, but the light returns, and so I'm sure someone more poetic than I can relate that to the tragedy that happened down there. It's so random. Yeah, yeah. I've been meaning to. I have made a list of all the high schools that have planetariums in this area, and I've been meaning to reach out to each one of them to see if we can collaborate. Obviously, they don't need our inflatable planetarium, but they may not have telescopes that they could utilize. So maybe come up with some kind of joint event. But yeah. But thank you. Yeah, I'm very excited about the Evaldi thing. I really want to make that happen. My director seems to be, I think, is fairly lukewarm on the idea. So I might have to get creative. But we'll see what. Yeah, I'll definitely bring it up to Paul and see what he has to say on it. Maybe he will be more excited and will make it more often, more likely to happen. I am fading. Shit. What's going on over here? Nothing of any note. Someone says that what's in his claim that there's no way to falsify Aether. Mm-hmm. Right. So what else is going on? What else is going on? So yeah, it's finals for me. I have a ridiculous amount of grading, particularly labs that I need to do. So yeah, I don't know. Doing this was probably not the best use of my time, but it's fun. So I will try to get up as early as I can to get those labs graded. I should be done by Friday. And then I can concentrate on YouTube content. And I want to restructure my 103 class, because of course I do, such that the class is, because now I have basically a library of lectures that cover the material. And so what I want to do with the class time is I want to focus more on the critical thinking aspect of things, of like I was talking today in the lecture, Neptune was discovered through wobbles, for lack of a better term, wobbles in Uranus's orbit. And so take something like that and kind of approach it from a classic scientific method sort of approach of, all right, we see these wobbles. Um, so make a hypothesis as to why that is the case, and you know, hey, maybe there's a mass out there tugging on it. And if that's the case, then what should we expect to see? And that sort of thing. So try to find instances in astronomy where I can do that, where I can focus. So the the lesson is more geared towards teaching critical thinking and using astronomy as an example. Because ultimately, with this class, and I don't know, I would say that teaching students at that level critical thinking is more important than teaching them astronomy. I could be very wrong about that. It is 2 in the morning, but I don't. I definitely think that teaching critical thinking is. I haven't been emphasizing that as much as I want to in my classes. So I think I'll take that. I certainly am not going to try to make it active learning. I've learned my lesson on that. That was a complete disaster last year. Yeah. Pro tip: if you've got 200 plus students, don't try to invert the class. It's not going to work. Oh man, apologize for apologize for yawning so much. Let's see. Oh, Rachie, morning. I was wondering if I was going to be at this long enough that you might wake up and pop in. Funny, I've heard Witson say that they made the globe unfalsifiable at this point, and if he made a claim that was unfalsifiable, yeah. I'm going to be having a conversation with him this Friday, so we'll see how that goes. But thanks for popping in. I can show you. I need to stop yawning. I can show you a couple things that we did tonight. Let's do that one. So I did some imaging early on. That is the morning. This is the Whirlpool galaxy. These are rough, raw images. They have not been calibrated. They have not been processed in any way. I'm hoping to make pretty pictures out of it. So that was M51. And then after that, I somehow got convinced to do M65, which is another spiral galaxy, which I know that doesn't look like much, but bam! You can see, hopefully, whoops, it's not what I wanted to do at all. Stupid Windows 11. All right, download. Come on, Maximum deal. Figure your stuff out. All right. Anyway, it's a spiral galaxy. It's got this lovely dust lane. It's got this extended region, which I'm hoping to bring out. Yeah. So that's basically what I've been doing for the last 5 hours. So if you're curious on what it was like for me to take these images, go back and skim through the live stream after I'm done. Yes. That is what unfalsifiable means. There's no way to test it. Like string theory at this point. Oops. going on? Black and white images. The Galaxy one looks bright. Yeah, well, those were both Galaxies, actually. You're probably talking about the second one, M65. Yeah, because it looked bright because of really the scaling of it, scaling of the image, and it has a very pronounced bulge. So a lot of stars basically packed in the center of the galaxy, more so than what am I doing? I can just show you. So here you have two galaxies. You have the large spiral galaxies actually eating this one. Once I get this all snazzy and process and stuff, you'll actually be able to see that there is, in fact, a stream of materials coming off this particular galaxy and then streaming into that one, into the main galaxy. This is an example of what we call galactic cannibalism. It happens more often than you'd think. Galaxies slam into each other because of gravity. And what am I doing here? So yeah, the bulge is the central region, which is a concentrated. Basically, you have a centrally concentrated mix of a lot of stars that are localized, so that gives it the brighter appearance. But yeah, there's a lot of little factors in play. Maybe a lot, but there are multiple factors in play as to why this image looks the way it does. Which hopefully I will do a stream sometime next week, maybe this weekend, where I take all these images, I calibrate them, and I try to make something pretty out of it. We'll see. What would it take to make it all pretty? So I've got to calibrate them. I've got to subtract off the darks, which because I'm taking 100 darks that are exactly the same exposure as my science images, I don't have to worry about the bias. So I mathematically subtract off the darks, and then I will divide by the flats. So I get rid of all of the signal that is due to the detector in the optical system. Like, for example, this little squiggly alien dude, get rid of him or them. And that's the first step, is to calibrate the images. Then I will stack the images on top of each other. I took about 10 of the Whirlpool Galaxy in blue, green, and red. And I took 5 of M65 in blue, green, and red. I will stack those, all the greens together, all the reds together, all the blues together. That will hopefully bring out more signal, and kind of tamp down the background noise. And then I'll have blue, red, and green. And that's when things get a little bit more interesting. So I'm going to try to process them some way. I'm going to look into using wavelet filtering. What that does is, roughly speaking, is an attempt to sharpen the image so you can see better detail, or essentially finer angular resolution. And so I'll do I'll play around with different filters to try to get those images as sharp as possible, and then I'll add them on top of each other. I'll make a true color image or a 3-color image. If you take blue, red, and green, slam them together, you get true colors. And then I will try my darndest to color balance it appropriately so that it will look like what you would see as if you took the Enterprise, went out there, and looked out the window. Hey, Liam, I haven't seen you in a while. Howdy. Would the globular appearance of the smaller galaxy be because it has involved in previous... not previous mergers, because of this merger. So I don't know. To me, I haven't read any of the papers on it to know specifically. But my guess is, just by looking at it, that smaller galaxy was spiral initially, but it could very well have been elliptical. But yeah, the fact that it's small like that is more than likely due to that that merger that's going on right now. If it were a product of a previous merger, I wouldn't expect it to have any kind of roundness to it. It would be very, very irregular. Um, mhm. Yeah. How do I know? So right now, I am taking a flat, and what a flat is an image of a. In this case, it's the image of the inner part of the dome, um, and is so out of focus that basically it's just a illuminated panel. And so what I can tell you is that anything I find here, this like little squiggly bit, um, if I find it here and I find it, I should just keep it open. And I find it in my image, then I know that, and it's in the exact same spot. It looks exactly the same. Then I can be confident that that little doohickey is actually in the optical system and not astrophysical in nature. The other reason why I know is because I've literally looked at the CCD, the plate, and I can literally see the little fragments of cotton ball that were used. I haven't really given a good test of the tracking. I can tell you with confidence that I was doing a 3-minute exposures tonight, which isn't great, which isn't really long, and there was no tracking issues. I know some photo students have been doing longer exposures. I think. I don't know. They've definitely taken a lot of data, but I don't know if they've taken a really long time exposure. But one of the things that is on my list of things to do is once I have access to the telescope again, I'm going to um, do a tracking test. So, well, actually, one of the things that I want to do is I want to put this thing through its paces. It's been 3 years. I'm way overdue. I want to check the linearity of the chip. I want to check what the actual dart current is. I want to check what the gain is. And if I haven't already said it, linearity of the chip, and then also the tracking and all that kind of fun stuff. So, all right. First line, go to LIGO, compare with the war that met to the next to it. I think it was. Let's fix up this. I think claim. LIGO. I really wish we talk more about the actual observations of LIGO. I find that to be much more fun to talk about. I used an interferometer. I use the Chara interferometer. It's baseline. It's not. LIGO is way bigger. It's the arms are 4 kilometers. Am I done? I'm done. Woohoo! I can go to sleep. But I use an interferometer. I can tell you that the tubes were straight, level, I guess, perfectly straight. But the topography on Mount Wilson is ridiculous. So curvature, I don't think was really a factor because because it's on top of a mountain. You had ditches and gullies to worry about. All right. So what I'm going to do now is I'm going to put the telescope to bed. Shut down. Park. Telescope. Set up. Warm up the CCD camera. So there is the telescope. there is the dome. There's the control room, which I am not in. I am in my office 3 floors down. And here's the base of the telescope. So, woo! And this is the park position. This is the position we leave the telescope in after we're done with it. Okay, good. Dome is closed and put away, so I can kill that. I can kill that. I can kill that. I can turn the lamp off. Disconnect that. Kill that. And now, I will wait here until this sensor temp gets to roughly 0. So right now it was set to negative. The chip was cooled down to negative 25 degrees Celsius, and right now it's at negative 9.4 Celsius, 9. So when that gets to 0, I'm going to shut that off, and then I'm going to shut the stream down and walk home and go to sleep. So yeah, I've been at this for 5.5 hours. Oddly enough, this is, if this counter is correct, more people are watching now than were watching at any singular point along the stream, even when I started it. All right, so what do we got here? Forced the line is nonsense. You would have to use either optics or GPS to make the line straight. If you accepted either optics or GPS, we'd be done already. How about the old Tiger Dan special? Use publicly available flight times as a proxy for the distance between cities. Plot them up and build a map. Hey, if you become a patron of mine, one of the benefits of being a patron is, depending on what level you are, you get access. I will give you access to the telescope. So I'm being facetious. Or am I? I do have a patron account. I do. That is a bonus for it. The first level, if you're the lowest level of patron, which I think is $3 a month, you get to name my firstborn, assuming my partner agrees to that. So far, the 2 patrons I do have declined that opportunity, but yeah. If you and your family are ever in the States, Rachie, we do public nights. So if you're ever in the Washington D.C. area, hit me up, and I will be happy to give you a private tour. You and your family, a private tour of our observatory. More practically, I will try to do more of these live streams. Over summer, the telescope is less subscribed, meaning that we only do research observing primarily. There's no teaching over the summer. So it's easier for me to get my grubby hands on it. Oh, that's done. So we're going to do that. We're going to disconnect. That's going to go bye-bye. Bye-bye. And then I'm going to VNC out. And haha! Infinite window! Inception! All right, yeah, I really need to go to bed. So, yeah, thank you all for being here. I really wish we could go further, but yeah, I am tired, I am hungry, and I have stuff to do tomorrow. Yeah, maybe next time I do this, And there will be next time. Maybe next time when I do this, I will start the stream at midnight and go for the second half of the night. That way, anybody in the UK or further along can watch at a reasonable hour. So, all right. Peace out, clear skies, and I'll see you later.